All right, let's get started. So I'm going to ditch the mic right off the bat. I'm not going to pretend it's going to work for me this time. So let's get started. Day 3.
Are you recording?
Let's. Yep, I'm recording. All right, thank you. Day 3. As the slide says, we're almost there. I know we're all tired, grinding for this damn exam, but tomorrow's the day. Y'all are going to be fine. Y'all are going to do good, and you're never going to have to think about it ever again, unless you're up here doing a workshop for one like we are. But it'll be over. You guys are, take that deep breath. Everything will be all right? So for today, we're finishing up with binary and bitwise, as well as other base number systems like hexadecimal, octal, whatever. We're going over binary search very briefly because that's technically one of the topics that can show up. We're going over heaps, we're going over tries, we're going over hashing, and then lastly, we're going to go over permutations, which I failed to do last year. I won't make that mistake this year. With that being said, let's go ahead and get started. So, first on our agenda for today, we've got bitwise and bases. By show of hands, how many of you in here are currently in or took discrete with CS1? All right, how about CDA, comp arch, logic, whatever? All right, so you guys have done this a few times now, right? You do it in discrete, you do it in CS1, you do it in CDA, right? Albeit maybe it's more than binary in CS1, but by the very minimum, you've worked with binary in those classes before. And so essentially what binary is, along with hexadecimal and other things, is more of a math-heavy concept, but we can kind of exploit those math concepts to do some really fun programming stuff, right? So what a base system is, essentially, what do our digits range, right? So for decimal, we're pretty familiar with that because it's what we use in our day-to-day lives. It goes from 0 to 9. But notice how we call decimal base 10. Now, because that doesn't mean it goes up to 10, but that's because there are 10 digits, 0 through 9 respectively, right? And so some of the common bases that you're going to see in terms of computers are going to be decimal, which is base 10, binary, which is base 2, and hexadecimal, which is base 16. Perfect. These come up a lot in computers because a lot of the architecture we use is based around them, but for the purposes of CS1, you're also relatively expected to know how to convert to and from any type of base. Base 7, base 5, from base 4 to base 8, and I'll get into all of that. But that's essentially what a base system is, right? So I use sort of a wild card here and just say base X, right? Forget 10, forget 2. Oh, I swapped the wrong one. Forget 10, forget 2, forget 16. Just consider this as base X, right? And so X is going to represent the possible digits that we can have, the number of them. And so you see in hexadecimals, we sort of flub into the alphabet and go all the way up to F. So just think of digits as kind of characters and more so, right? So like I said, for decimal 0 to 9, it's base 10, binary base 2, so on and so forth. But essentially what it is the value of each digit is going to be num I times x to the I, where I is the starting position and x is the base. So by that I mean it sounds kind of like a messy formula, but for instance right here, this is 3, right? So our position is 0 in this case. We're going from right to left, right? So this is our 0th digit. So it's multiplied by x to the power of that index. So in this case, this is 16 or whatever. For this is a base 16 example. So it's 3 times 16 to the 0, right? And that's going to yield us our value. And what this is up here is this is just them evaluating 16 to the 0, that 1. In this case, 16 to the 1 is 16, so on and so forth. So that's kind of how you can think of bases in any arbitrary way, is sort of like base X. So imagine if this were, let me see if I can go here. If this were base 7, we could do, let's see, 5, 3, 1. Base 7. To get the decimal value of base 5, that's going to be 5 times what? 7 to the 0, because this is the 0th index of the actual number. This would be 1, and this would be index 2. So what would the value of this position be? It would be 1 times, any guesses? 7 to the 2, correct, because our base is 7 and we're at index 2, right? So this is how I like to think of it, as like a base x, just because you can try memorizing each particular base and its rules, but it's not going to help you succeed because you are going to be asked for different bases that aren't within the typical computer system that we're kind of familiar with. So that's base x for you. So converting to decimal is exactly what I was describing to you. You essentially want to take each position, and so this is binary as this example. This position, we take the value and multiply it by base to the power of that index, which in this case is, here, let's make this a little easier. So in this case, this is, again, index 0, 1, 2, 3, 4, 5, 6, 7. This is our indexes, right? So this value right here, we derive it from this value times 2 to the 0, right? So that's 1 times 1, which is just 1. This is 1 times 2, so on and so forth. And we can see right here, this is a 0. So it's actually 0 times 2 to the 2. But regardless of what this is going to end up, a 0 is just a 0. So we actually don't add it. And so this is a unique property of binary, which is why computers rely on it. Notice how in things like base 7 or base 4 or base really anything other than base 2, there are a range of different values. But with binary, it's either a 1 or a 0. You can almost treat binary as a toggle between true and false, right? Which is what we're kind of like drilled into our brains a lot. And that's why computer architecture really likes binary, because if you think about it, all of these gates that we're operating with have an on switch or an off switch, electrical signals, right? And so that sort of mindset of either it's on or it's off is a really powerful concept that you need to remember when we get into bitwise coding problems later on down the line. And so in the same manner, a 0 means we're not adding this position, and a 1 means we are. So that's pretty straightforward in terms of binary, but things can obviously get a little more complex because when we're dealing with like base, I don't know, 5, like 1, 2, 4, this 4 actually has a much more complex value than add it or not, right? Because this would be 4 times, if this was base 4, or no, this can't be base 4, it has to be base 5. It would be 5 to the 0, which is, in this case, 4 times 1, which is 4. But this over here would be 1 times 5 to the 2. And that's, you know, it can grow in complexity a lot more than something like binary. So that's just something to keep in mind. And then, obviously, we need to know how to do it the other way around. We can't just go forward. We need to go backwards. So the way that you convert a number from decimal into whatever system, and again, this is base x. This example is base 2. You are basically going to, so back here, right? You know how we start our actual addition from right to left, like our indexes increase from right to left. So the same kind of happens here where we're building it from right to left. So what we do is we take the base and we divide it. We take our decimal number and divide it by the base, and its remainder is what the position is actually going to be at that specific index. And we build it from right to left. So in this case, for base 2, it's a lot more easy to see because there's less going on here. But if we go, our first number here is this 0. Our second number is another 0. Our third is a 1, so on and so forth. So as you can kind of see here, we're building the number from right to left, right? So that's an important thing to keep in mind because I see some people build their new base numbers from left to right. It's like intuition, and that's wrong. So you perform the first operation to prime the number. So that first division is going to give us 100 over 2, which is 50 plus 0. This is the way I like to think about it, that extra plus being the remainder here, because when you get to more complex bases, the remainders might be a little more, you know, like bigger and whatnot. So we place this 0, and then we do the same thing again. So 50 over 2 is going to give us 25 plus 0, which is this 0. And then the way we do this here is we divide 50 over 2, and the answer is going to be 12 plus 1, because the way that you should look at it is we know 25 over 2 in a continuous number system is 12.5. But if we have that, we always just want to go, we want to seal it and just turn that into a remainder. So this is that 1. And then again, this is going to be 6 plus 0 because 12 is evenly divisible. And that's where all of these digits come from, right? Does everyone see how we do that? Any questions before we move on? All good? All right. The first one? Oh, all the way at the end? So, because you could imagine, so like some people just break early and don't do that last operation, but if you do 1 divided by 2, that's equal to 0.5. And we want to always seal, so that becomes a 1. So that last digit, you could almost like, if the digit, so like if the actual digit is less than the base, you could just say, okay, I'm calling it quits, because that's, if you think about it, if you divide that number by the base, it's always just going to give you itself. That's like a math identity, right? All right. And so let me go over a shortcut. And if they do give you, if they give you a base conversion question, it's obviously not just going to be 1, because on the magnitude of some of these problems that we've seen, just one bitwise isn't enough for them to feel like, okay, this person knows what they're doing, right? So they're going to give you multiple. And usually if they give you that, one of the examples is going to be a perfect base of 2, each of the bases, and you're going to have to convert. So by that I mean convert from base 2 to base 8, or base 4 to base 16, or base 2 to base 8. I already said that. Base 2 to base 16, right? What do all of these numbers have in common? They're all bases of 2. So this is 2 to the 1. This is 2 to the 2, 2 to the 3, and 2 to the 4. So if they ask us to convert between two base systems that are perfect bases, perfect powers of 2, there's a little shortcut we can do that I'm personally a fan of. Anything to save work on this FE is more time you can get partials on other things, or just finish it entirely, right? So you want to do that when you can. So you want to express one of them in binary, right? Ideally, they'll ask you for one that's already in binary, like the base 2 to base 16. But if not, you're going to have to do it a little backwards here. So essentially, you're going to divide here. So in this case, it's already in binary for us, right? And so this is 2 to the 1. For base 8, we can say that base 8 is 2 to the what? 3? So the way that this shortcut works is you take however many digits that this is, this power, right? So in this case, we want to take the digits, 3 of them. So these 3, and these 3. And imagine if we had like one more here, you would always pad with zeros, and you would take that, right? But we don't have extra ones. So this perfectly works out for us. It's a bunch of 3s. And so what you can do is you can actually convert, and it shows it right here. You can convert each of those, I'm going to call them Y-sized chunks, into that new system, because they'll convert that way. So like if we had, let's say for example, we wanted to convert this to base 16. Let's do it this way. So I'm going to do base 16. So imagine this was 16, which is actually just 2 to the what? 4. So we're going to take these 4, and then we're going to pad this with 4. And so this first chunk, 1, 1, 1, 1, is 1 plus 2 plus 4 plus 8. And as you notice here, this is going to give us 15, which is the maximum number that you can get in hexadecimal, which is F, right? And so you kind of saw right here how if we have a completely full binary representation, because you can count all ones as full, it actually corresponds to the full version of a hexadecimal digit, which is F, right? And so if we move on to 0, 0, 1 right here, that is just 1, right? That converts to the number 1 plus 0 plus 0 plus 0, which in hexadecimal is still just 1. And then if we do the same thing over here, it's also still just 1. So this is what that number would equal in base 16. Do you guys get what I mean by perfect powers and grabbing Y digits? Does that make sense? All right, awesome. So now that we've reviewed base systems, I think I'm finished. Yeah, okay. So we've gone over our number systems, right? We've described what number systems are. So now the question is, why do we care about this as computer scientists? Why do we want to use this in our program at all? And the answer really is there are a lot of really clever algorithms that exploit the on and off manner of binary digits to make some really complex and kind of like shortcutty algorithms that are super concise. And so that's kind of why they want to do it on the foundation exam. They think a lot about your problem solving ability, because a lot of what programming is you're solving problems. But you'll notice on Bitwise problems in the foundation exam, they're just making stuff up. Like, they're really trying hard to make a problem that would apply to Bitwise, right? So what I like to talk about is, like, how do we actually use this? Because that always helps me in my head. Bitwise is extremely important in the real world in software engineering for memory efficiency, right? If you think about it, we can store so much information in just one 4-bit integer, right? We could have a map of true and false. Because a lot of the times, maybe if you're working in web development, you're going to have to send information over the internet. And some of these packets that you're building can be really, really large. Just by exploiting, taking it from maybe 16, imagine we're sending 4 true or false values over the air, right? Which is 16 bytes. Why? Because it's a 1, 0, 1, 0, whatever, stored as integers. We can instead store one number over the air and extract with maps each one of those positions, and we've cut our memory costs for that specific function in our application by a quarter. That's a significant deal. And so that's where binary and Bitwise come up a lot in the real world and when building real applications. So that's just a tangent of mine. If you like thinking of things that way, cool. If not, sorry for wasting your time. So these are the Bitwise operations, right? These are the actual programmatic pieces of code that we get to use when handling Bitwise kind of problems, when tackling them. And so there are kind of 6 main operators, right? And alone, they are pretty straightforward. There's nothing super complex about these operators. A lot of the heavy lifting of a Bitwise problem is you trying to change your frame of mind to think of it as a Bitwise problem. So that's why my personal recommendation a lot for Bitwise is actually doing practice problems, because you need to start seeing problems as Bitwise, right? But anyways, and we'll take 2 bits and set them to 1 only if both of them are true. So in this case, 1 and 1, cool. And then all of these are not true. Note that they both have to be true, not both be the same. 0 and 0 is still 0, right? Or either of them have to be true. We've done this same logic already in our expressions and if statements and while loops. It's the OR operator, right? It's only just one of them this time. This is the binary OR operator. Same kind of structure. And then XOR is only if one of them is true. So in the case that both of them are true, this is false. Both of them are false, obviously false, but if these two, only one of them are true, it's going to yield a true value, right? And so these are really good to sort of visualize problems. The other 3 that are important are the not, left shift, and right shift. The interesting thing about the not operator is you actually don't apply it between 2 numbers. You apply it to itself. This basically just flips all of your bits and toggles everything in that specific piece of data that you've passed into it, right? So the not, it just flips everything. So in 1, 0, 0, 1, it gives you 0, 1, 1, 0. And then left shift and right shift is essentially going to take all of the bits and move them to the left or the right by k times, right? So in the instance of 1, 0, 1, or 0, 1, 1, 1, 0, 1, if we performed a left shift by 2, then each of them goes 2 to the left. So it will go 1, 0, 1, 1, 1, 0. And so note that everything that gets replaced is going to be more zeros. You always want to pad with zeros. At least in this case. If you've done any of those weird algorithms in Comp Arch, obviously there's different approaches, but when it comes to just standard implementation, it's just going to drop off certain numbers, right? And so in the case here, everything to the left of these 3 ones, notice that this 1 right here and these 2 zeros, they went off the edge. They went into the void. We don't care about them, right? The same is true for a right shift. If I were to right shift this by 2, these 2 bits, gone, and zeros would be filled in here. Right? So that's just something to keep in mind. But the other really unique property of left and right shift is shifting left, assuming that there's no fall off or overflow or whatever, it's actually going to be multiplying the number by 2 to the k times. And the reason that is because if you think about it, let's say I have 0, 0, 0, 1. This is 1 times 2 to the 0. And if I move it this way, it's going to give us 0, 0, 1, 0, which is 1 times 2 to the 1. And so this happens for every digit. And so you can just multiply the entire thing by a constant factor. This is a difference of 1. And so it's by a constant factor of 2 times 2 to the power of k, right? And so that's a really unique property. And then if the left shift makes it bigger because we know going to the left increases our magnitude, right shifting does the exact same thing but opposite and divides the number by 2 to the k. Not 2 to the k times, just by 2 to the k. Apologies for that typo there. And so now we need to start talking about kind of conceptually understanding things. Even though 167 is in decimal, your computer under the hood represents all of these numbers by binary by default when you're running your code. And so when you get a bitwise problem and they pass in 32 as like a bitmap, it's like, what does that mean to me? Well, you're actually going to try and like squint really hard and look through this code and really see what the machine's doing. And you're going to have to represent them in binary. So for a lot of the cases that you run through in some of these problems, it's best to convert, like they'll give you like that example, right? Well, they'll say, we'll pass in this and we'll get out that. It's a really good idea for you to take those numbers that are probably going to be in decimal and represent them in binary and try to figure out what they want from you, right? And so 167 is represented as 10100111, right? And so again, you kind of want to think about it like this. And so right here, right, when we do the OR operator on these 2 whole number decimal integers, it's going to give us 191. And so it's kind of hard to like find any rhyme or reason about why 167 or 29 gives us 191 without trying to think about it in decimal. So that's what I'm saying. You need, like, for these problems, you need to sort of shift your mindset to the whole other number system. And so again, we can see this here, right? For 167 and 29 somehow goes all the way down to 5. Why? Because binary. But if you didn't understand that binary representation under the hood, you'd have no idea why that even happens, right? And so here, right, we have 186 for the OR operator, 88 for not num1 because we're toggling all of its bits on and off. And then left shift, right? So we're left shifting 5 by 3, which is the same thing as multiplying it by 2 to the 3, which is 8. 5 by 8 is 40. So 5 left shift 3, if we print that, it's actually going to parse back into an integer and represent 40, right? So again, this is kind of how you have to start thinking about things when we're working with a binary problem, all right? And so that takes me to the questions. I didn't change the title for this. Okay, we'll start with this one. I don't know if anyone's seen num bits on, but I think it's the lowest solved foundation exam problem out right now. So we're going to do that together just to show you how fun bitwise problems can be. So let me move back to here. And so this is kind of one of the things that I was talking about. See how there's just a ton? This would actually be a 10 pointer. I usually include that at the top, but I forgot to this time around. So let's just go ahead and get started, right? So we have 347. We're converting from decimal to another base. So do we remember what kind of strategy we do here? Are we multiplying and adding or dividing and remainder? Dividing and remainder. Good. So we're going to start. The first number is going to be 347. We're going to find mod 5 here. And that's actually going to give us, since 2 is greater than 5, we could just say the very first digit on the right is going to be a 2, right? And we know that because that's going to be the remainder of this operation. So let's take out that remainder, 345, and then divide by 5 now, since we already extracted the remainder. So 345 over 5 would be, I'm shit at math. That's a 9. 300 divided by 5 should be 60. Awesome. So we have 69 now. So we take that over, we move that to the next digit over here. We're going to do that same thing again. So we're going to take mod 5. And what's going to be that? We know that 9 is 5 or 4 greater than 5. So we can put that on up here. And that's going to be 4. And that's going to give us 65. And then we're going to do 65 divided by 5, which should be 13. Yep, 13. And so then we go ahead and do that and iterate down. So now we're left with 13. And again, we know that 13 mod 5 is going to give us 3, since 3 plus 10, right? So 3. And then we're going to take that and we're going to divide by 5, which is going to give us 2. And so now the question coming from the right, how do we know that we can just stop at 2? Because 2 is less than 5, so we can just throw it up here. But just to proof it, 2 mod 5 still equals 2, right? Modulus identity, if you're taking the mod of a number less than, it's just going to equal itself. So that's the answer right here. Don't do what I'm doing and erasing my work. You want to show your work for these problems. They will award you points just to see that you had the right idea, right? So always leave your work here. I'm just low on room and this pen is chunky, so I'm going to leave it as that, right? And so for the next problem, so now we're converting from a base into decimal. So what type of strategy are we going to do this time? Multiply and add up, right? So the way I like to do it is I like to spread my numbers out quite a bit because we're doing some math here. So this 1, what is this 1 actually going to equal? 1 times 1 times 1. But think of it as 7 to the 0 for now, just so you can keep track, right? This is going to be 6 times 7 to the 1. And this is going to be 3 times 7 to the 2, which will drop down here. So this is going to be 7 plus 6 by 7 is 42, plus 3 times 49, which should be 120 plus 27, 147. And so we add all that together. That should give us 154, 156, 196. Sorry about that. I was adding all the digits in my head. I'm a mental math guy. All right. So here we go, right? Now we have this. This is all good. We're all done. So now we have another one of those problems where we have this conversion going on here. So we're going to need to represent each of these digits into binary, and we're able to do that pretty straightforward. So this digit right here, D, and I always get confused with hexadecimal, so I always write it out. I forget the letters. 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Right? And so we have D. D is going to represent, I'm blanking right now, a number in decimal system here. Yeah, it should be 13. So we're going to have 13. A is going to equal 10, right? And then 3 is going to be 3. So now I'm going to express each of these in binary digits. So we're going to start at the end in case we have any bits we can drop off. So 13 here we should be able to represent, and we know that we're going to be able to represent it in how many binary numbers? 4, because of the base here. This is 2 to the 4. So 13 should be, if it's an odd number, it'll always have an on bit here. That should be, what, 8 plus 4 plus 1? So no 2, yes a 4, yes a 8. This is going to equal 13. So I'm going to put this over here. For the next number, that should be 10. So that should be 8 and a 2. So that's 0, 1, or 1 for the 8, 0 for the 4, 1 for the 2, 0 for the 1. So this is 1, 0, 1, 0. And then this right here, 3, should just be 2 and 1. And so realistically, we can do 0, 0, 1, 1, but all padded zeros to the left are irrelevant. We don't really need those. So that's what our number is in base 2. And then same sort of idea here. We're going to convert this again into binary, and then from binary into base 4. What's up?
John, you said the zeros would be padded, but let's say you write them down, you still get the right answer.
You'd still get the right answer, yeah.
Dylan, I messed up something in the first problem. It's
I did?
supposed to be 190.
Yeah.
Yeah. You might want to head back to.
Is my math bad?
1 times 7 is 0.
One times. Yeah, that's supposed to be 1.
Oh, oops about that.
Someone pointed that to me.
Good catch. So this is actually supposed to equal 1. 7 times 7 to the 0, that's 1, so that gives us 190. Sorry about that. All right, so down here, we're going to express this again into our binary digits, each of them. We're going to express that. So each of these digits are going to be how many binary digits? 3, because this is 2 to the 3. So we're going to take 2, 4, 7, 3, 2, 1. And so we're going to go from right to left. So 1 is just going to be 1. 2 is going to be 2. And 3 is going to be equal to, that's 3. 7 is going to be on for all 3, so 4, 2, and 1. 4 is going to be just the leading bit. And 2 is just going to be the middle bit. Right? So now we have this here. And now, how many binary digits are we going to take at a time to go to base 4? 2. So we're going to grab each of these bits, and then we're going to go left to right. Or right to left, apologies. All right, so 1, that's going to give us 1. 0 will give us 0. This should give us 1 as well. This will give us 3, because that's 2 plus 1. This will give us, right here, this will give us 2. 3, 0, 1, 1. Right? Everyone see how we got that? All good? So does everyone understand going from decimal to another system to decimal, and the binary middle layer trick? All good? All right, cool. These should be a relatively simpler problem on the foundation exam. Was there one last semester? I don't remember.
There was a Bitwise problem.
There have been a few Bitwise in a row, so hopefully you guys get one of these. So yeah, someone caught my error here, because that should just be a 1. So we got 190 here. Oh my goodness. We got 190, 2342. That's good here. All of these are good, right? And so did they explicitly ask us to do the intermediate step to base 2? They didn't. So for whatever reason, I guess they want you to use that shortcut if you can. 1 point for intermediate step to base 2, 2 points for the final answer. Give any full credit for any valid process. 8 to 4 to 10 is harder but valid. Never mind, you don't have to do base 2. So they said this is fine. Leading zeros are not necessary for full credit. So that means you can have it or you can drop them. So that's the answer to your question. All right, so the next problem. This one's a fun one. Has anyone seen this one before in past years? All right, yeah, this one's an interesting one. So I think this one was it a 9% or an 11% pass rate? I don't know. It's on FE Prep. You can go ahead and see the pass rates for past exams. This is an 11% problem. So let's go through this. So again, this is a huge block of text, and I can guarantee you this is going to be like a few lines of code. This is the whole Bitwise mindset. They're going to throw something at you, and you need to figure out how to extract this into a binary representation and then apply some easy algorithm on top of it, right? So it's getting harder and harder to stay green while using computers. You decided that you will reduce your carbon footprint by storing fewer bits for your integers. Because if you think about it, a 1 bit is electrical signal, right? We're using too much electricity with all these damn 1s. So how, you might ask? You will store your integer plus some power of 2. Your goal will to be use as few on bits as possible in the resulting sum. This way you will have less bits on, just like turning off the lights when you leave a room. You'll be saving energy and the planet. Complete the function below so it determines and returns the least number of bits that will be on after adding a positive power of 2 to your number. For full credit, your function should be O of b time, where b is the number of bits in an integer. You're guaranteed that no positive power of 2 added to the original number will result in an overflow. So do you remember what I said, how that number falls off the end? They're just saying that you don't need to worry about that. Because if you did, this would not work very well. All right. So, for example, and again, they give us an example. So what do we want to do with our example they've given us? We want to represent it in binary. So this is an 8-bit number. We know that because it's going up to 6 here, right? And they go in 4s. So essentially, this number, 76 represented, is going to be 0, 0, 1, 1. We know that because power 2, power 3. And then 4, 5, 6. Wait. 1, 2, 3, 4, 5, 6. My 1's in the wrong spot. All right. So it can have 4 added to it to result in 80 right here, right? You see this? And so that is going to be, we're going to add. So how do we represent 4? 4 is going to be, this is going to be 1, 2, 4. And that's going to give us, let me pad the zeros, 80, right? So that's a 2 to the 6, which this stays, and we have a singular 2 to the 4. Wait. Resulting in 80. 2 to the 4. 0, 1, 2, 3, 4. No. Wait, I'm messing things up here. I should have started at 0, not at, sorry. So this is 0, 1, 2, 0, 1, 2, 3. There's an on bit in 2. 0, 1, 2, 3, 4, 5, 6. There you go. And we're adding an on bit to position of 4. So that 4 is right here. Right? And our resulting number is going to be 0, 1, 2, 0, 1, 2, 3, 4. 5, 6. All right. So let's start to kind of analyze here what happened, right? So we know that at the start we had 3 bits on, correct? And we added some base of 2, which again, adding a base of 2 is the same thing as doing what? We're adding a binary digit to some position, right? And in this case, that position is position 3, right? 0, 1, never mind, position 2. So we add plus 4, which is just 0, 1, 0, 0, and we're left with 2 bits. And so this requires an understanding binary addition and sort of the rules of binary addition here. So let me show you an example of what I'm talking about. Imagine we have the number 0, 1, 1, 1, and we add a 1 right here. Can anyone tell me what the result will be in binary? 1, 0, 0, 0. So notice how adding a bit at the starting position of a really long segment will negate that entire thing, and it will, it will carry over, like when you carry a 10 in decimal, all the way to this position. So how do you think that intuition is going to help us? How do you think that rule of binary can help here? So let's go back to the problem. I'm going to give you guys some time to think about it because I don't want to give this one away. So what do we think?
If there's 2 ones in a row, you can just add a 1 at the first one, and then it'll consolidate them.
It'll save you a bit. But do we want to look for just 2 bits in a row?
Or 2 or more.
So yeah. So if we have 5 bits that are on consecutively, and we add a bit to that position, it will turn all of them to zeros except for 1. So we go from 5 bits to 1 bit, right? So how can we use that logic to help us save the most amount of energy? Any takers? Come on. I can give it away if y'all want. Shifting's not the answer. You're close, because it kind of does that same. We're not multiplying by 2 to the k. We're adding a 2 to the k. Y'all want me to give it away? Back? Nope. No Zor. All right, I'm going to give it away. So we want to reduce the cost. We want to basically get rid of as many ones as possible by only adding one number, right? And we want to make that impact the biggest. So here's the algorithm that we could use for something like this. Imagine we had a number, and we know that this is kind of their intuition right here because they give us some code, right? This right here is essentially iterating over an 8-bit integer, right? That's why it's 8, because there are 8 bits in an integer that we can go over, right? And so we're going over here. We know we're going to be looping over each position. So essentially what we can do, and let me give a better example here. If we can iterate over this number, and we can find the longest sequence of consecutive ones, that is our target, right? We want to turn that off by adding a 1 at the start. So in the case here, right, we could do an entire loop over here, and we will determine that, hey, this is the longest running segment of on bits, right? So we can add a 1 at position 2 to the 0, which is adding 1. So if we added 1 to this, the new resulting number would be 0, 1, 1, 0. These would all become zeros, and it would overflow right here. So this would actually be 1. Do you see the intuition there? How are we feeling about that approach? Makes sense? So essentially what we're going to do is we're going to find the longest running sequence of bits, and whatever that number is, the number of bits we have on is going to be the total number of bits minus that length plus 1. So like, for example, this was 6 bits right here. And when we're done, that is 3 bits. So that is the 3, we would derive that from 3, or no, the total number of bits. So 6 minus 4, because remember, we eliminated these 4, plus 1. And that's how we get our 3 bits. Do we see how we're using that property of binary numbers to get that? All right. So that being said, I'll go ahead and start coding this up. So did anyone know how to iterate over each position to check for a 1 or a 0 in a number? You're going to use an and a what? A 1, an and, but you're going to need to shift it. We need to take that 1 and we need to move it over the position we're checking for. Because if we just keep doing and 1, it's going to keep going for the first digit. So there's 2 ways you could do it. I personally like shifting the 1, but you could shift your number to the right, or you could shift your 1 to the left. Either or works, all's fine. So we're basically checking, okay, if we have an on bit, we can check that if it's going to be our x, which is our actual number, and 1 left shifted by I. Does everyone see how we can use that to extract the digit? So here's what I mean. Or it does not equal 0. Sorry, because this could equal another number. So that we have a positive result from this, right? So the way that works is, imagine we have this right here, this number, and we have our, so we do 1 and, or 1 shift left by I and x. So the way that this works is, imagine that our 1 exists right here, and we're at index 0, right? This is going to return 0, because 1 and 0 is 0. So then we increment I to 1, which means now 1 shifted to the left by I puts 1 here. And so with each iteration, we're moving 1 to a different spot and checking. Do you see how that logic works for checking if the bit's on? Everyone good? All right. So this means we have a 1 bit, right? And this means we're going to add to our current running total, current plus plus, right? Because we have a 1 bit, so everything's good, right? And we're also going to increment the number of bits currently on, because we also want to keep track. Remember, we need to know the number of bits that were on in the first place. Oh, I erased the math. You guys remember the 6 minus 4 plus 1? So we need to know the 6, right? So we're keeping track of both if it's on. And if it's not on, what do we want to do? We want to say our current longest sets back to 0. Right? So this is our current. And then before we iterate, we're going to check if our longest is greater than current, then we're just going to make longest equal to current. And so you guys see how now we've iterated over everything. We have 3 things. We have 1, the number on. So in our first case, we would end up having this being 6. Our current doesn't matter in the end because this is just how we're keeping track of the longest, right? This is basically our current length, our current longest. And then if we get greater than longest, in the case of like those 4 ones in a row, current would be 4. I did this backwards. If current greater than longest. Because we're saying if this is the new longest. So if current is greater than longest, we can update it so that longest now becomes 4. And so then again, do you remember that formula we drew? We're going to say num on. And then what's the other 2? What's the 2 things we have to do here? Num on minus. So let's go back over here. Right? We did 6 minus 4 plus 1. So num on minus longest. Because this is the amount of bits we're turning off. But then remember that carry goes over and we add what? 1. So this is actually this counts how many bits are on. We're not actually returning the number that we create, right? Is that problem? Question?
Can you grow up a little bit?
Yeah, I'll zoom out for you.
Why are there 2 and signs in the first if statement?
Oh, that should be 1. I did ampersand. My bad. That should be a bitwise and. Yep, you're right. Because we're masking it. We're doing the and operator. Any other questions? What's up?
So, 1 left shift I, how is that read? Like you start at the first bit and then like I increment 8 times?
Already? What? Dude, it was at 90% when I came in. Can you give me the charger, ASAP? Thank you. This thing making me mad. I have a portable in my bag. Let's hopefully this doesn't die. So in this case, 1, I is going to start at 0, right? So 1 left shifted none is right here. And so we're going to take the AND operator, which is going to return 1. Imagine there's padding 0 to the left. And then we're going to increment I, which means we shift over 1 to this position. And then we mask and this is going to give us 2. So that's why I check does not equal 0. So if 1 left shift I does not equal 0, that means we've shifted over a bit that is on because it gives us some arbitrary number that isn't 0. See how that works? That's how we can iterate over every bit in a binary representation of a number and determine if it's on or off. Kind of makes sense? Yeah, well, it's so you could imagine this part right here is the shifting to the left part. So we're saying, does this position give us something when we mask it? Does this position? This would be I equals 0, 1, 2, 3, 4, right? So we shift the 1 to the left 4 times and then take the mask. And remember, when we shift it, we're just padding zeros. So we have the guarantee that if this doesn't return something, then the only bits right here is a 0, because that's the only bit we're actually observing. because we're moving that 1. Everything else is going to be zeros. So like, you know, if we did something other than 1, maybe we might have another 1 here, and that would be like a false positive kind of thing. Sorry if that's confusing. Does that kind of a little more sense? A little bit? Yeah. So that's how you iterate. There's a way you can do it backwards. You could actually do 1 and value right shifted I. Does that make more sense in like a little bit? Because then what we could do, imagine, so we have 0, 1, 1, 0, 1, 1, 1, right? And let's say this is our 1 right now. So right here. So this and right there, right? And then we take that whole number and we shift it down 1. And then we check that position, because again, it falls off the end. And then we check that position. And then we check that position. That's what the I is, the shift I. We're moving everything over the 1 so that the AND operator can catch it at that specific position. All right? Cool. So on to the next topic. Those are our 2 questions. All good here. So I'm not going to actually do this one because we spent a lot of time on Bitwise. But here's my point with Bitwise problems. Look at all of that. Look at all these words right here. Right? Painting fences, if we already painted it, we don't need to paint it again, and layer it and array it. And guys, like, look at this. This is 4 lines. All right? So this is kind of what I mean by Bitwise problems. It's a lot of thinking of things as binary, and then it's pretty straightforward once you convert it and change that mindset. What's up? The return statement? All right. So let me run through this problem super quick because I want to move on. So let's say we have 0, 1, 0, 1, 1, 1, 1, 1. And so we find out that this is our longest result, right? So we can add, and we don't even need to know what number it is. We don't even need to keep track of the position, but we can add 1 to this to give us, again, this is going to carry over all the way over here, and all of these will be zeros. It's going to be 0, 0, 0, 0, 0, 1, 1, 0. Do you see how I got there? Because we added 1 to this position, and then that kept carrying over all the way over to here. Do you get how we did that?
We're adding 1 to X?
Yeah, we're adding 1 at this specific position. Because the question is, what are the fewest amount of bits we can get by adding a number of 2 to the k? Which means basically adding a bit at any one of these positions. We don't need to keep track of what we're adding, but just any of those positions, right? And so let's keep in mind, this right here had 1, 2, 3, 4, 5, 6. This had 6 bits on, right? This one now has 2 bits on. So how did we get that? It's the length of our longest, which is 5. So 6 minus the length of our longest plus 1. Because these 5 bits go away when we add, but then that carry gets all the way here and adds another bit. So the return statement is asking, what are the fewest number of bits we have left over? So it's the longest running segment, or all of the bits in general, minus the longest running segment, which triggers that zeroing, plus 1 because it lands somewhere eventually. Got it?
So we're never actually like changing X. We're just
Some of them you might be, but we're not actually
in this problem.
in this problem. We're not, because they don't want X.
Yeah.
We could change it if we wanted to. It wouldn't do anything for us, because what they want is to know the number of bits left over if we're green, and we have as many bits down as we can. Got it? All right. I hope Leo's next. My voice is going. Okay. Any questions about bitwise binary? What's up?
Really, that paint fence question, is that a 10-point question or a 5-point?
I think it's a 10-pointer. 10 points. So that's the crazy thing about Bitwise. Again, a lot of the points you're getting awarded is that mental heavy lifting, right? And as you can see here, we're doing that same shifting again. So we're shifting it over by I, and then the result, we're ORing it, right? And so in this case, we actually are returning to the right side of the room. We're actually returning a number that we modify. So if you look at this problem, I'm not going to go over it, but just know that that's a possibility. All right, I'm going to hand it off to Leo. I'm going to go run to the bathroom. I'll be back. Hope that makes sense.
All right. Give me a moment just to settle in, and we'll get started. So, unlike Dylan, I am a microphone enjoyer. So until it proves me wrong otherwise, I will keep using it. So give me a moment to get it on. Okay, can you hear me all right? That does not sound good. Anyone have a problem with the mic? If you do, raise your hand. Okay, seems like it's good. Yeah, okay. So we're gonna go over binary search next. Now this one doesn't actually have any problems on it, so I don't think there are any problems that actually show up on the foundation exam that are directly correlated towards like asking you something about binary search or coding a binary search. But the concept of, I can't with the mic, I'm sorry. That was really fast. Maybe this was just a bad one. But the concept of binary search is on the exam, so it's important to go over it. And it's not too much. We just have 2 slides for this one, and then we move on to the next. So, anybody here know what a binary search is? If you do, raise your hand. Oh, not a lot of people. Wow. Okay. So, essentially, what a binary search is it's an extension of a type of algorithm called searching. So, as in the name, it has search. So, how many of you have heard of a linear search? All right. So, around the same number of people. But a linear search is just around going through an array and looking for an element that you need to search for. And when you find it, do you have a question or no? Never mind. Okay. So it's just looking over an array for an element, and once you find that element, it's going to return that element and you're good. But if you have to look through an entire array, let's assume the array has n elements, then it's going to be O of n for your search. Now, binary search is a clever little algorithm that you can use on sorted arrays, only sorted arrays, to make your search logarithmic. So instead of having to do a linear search in O of n, it would take O of log n to find your element. Now, this only works on sorted arrays. I'll explain in a moment why. And how it works is you start by picking the middle element in the array. And because the array is sorted, you know that everything to the left of this element is going to be less than it, and everything to the right of the element is going to be greater than it. So using this logic, if you see that the element you're looking for, so let's say in this list you're looking for the number, actually they are looking for a certain number, so okay, let's say we're looking for 38. So we get the middle element in the array, and we see it's 16. So we know 38 is greater than 16. So now we know that everything before it is not in our list, or doesn't have to be searched, because 36 or 38 is not less than 16, and everything to the left of 16 is less than 16. And because of this logic, we get the approach of basically cutting the list in half every time until we find our element. And that's what gives it its logarithmic behavior. So when we check 16 and see that 38 is greater than 16, now we ignore this entire section, and we have essentially a new list, a sublist, where we have our 23 as our starting element and 91 as our last element. We take the middle of that, which is 56. And now we see that 56 is greater than 38. So that means 38 must be to the left of 56. So we do the same process, and now we look through, so it cancels out these 3 elements, because we don't have to look here anymore. And depending on how you find the middle, there's probably integer division here. So it found 23. And 23 is less than 38, so 38 must be to the right of 23. So just cancel this element right here. Oh. Wait, what happened?
Weren't you using the iPad?
No.
Oh, my bad.
Yeah, no. No, yeah, I was not. All right. Let me actually move the iPad to where I'm at, just in case. Wait, was there once? Oh, that's just on here. Yeah, I could come back to this and no, I won't. It's okay. Raise your hand if you're confused right now. All right, we're good. So yeah, we see that 23 is less than 38, and because of that, we have to cancel it out, and then our list just becomes the one element that's 38, and at that point, we know that we found our element because 38 is equal to 38, we just return it. So it cuts the list in half repeatedly until it finds our element, and let's say the element isn't in the list. What happens is we eventually get to a point where our start point is greater than our end point. And what that means is that, well, we don't have a list that we're searching for. So binary search operates by having like a start point and an end point. That's what these numbers above here kind of mean. So I think L stands for low and high stands for, or H stands for high, and M is for middle. And when your low is greater than your high, that means you could get out of the loop, and usually when you don't find your element, you would return -1. But if problems do come up with concepts, they'll tell you what you need to return or anything. But then again, there aren't that many problems that relate to binary search on the FE. Okay, so let's look at some code, and then we'll be on our way. So first, you have the array, you have the size of the array, and then you have the element you're searching for. You have the left, which represents the start of the array, 0, and then the right, which is size -1. So while your left is less than or equal to your right, because remember, if the left is greater than your right, that doesn't make sense. You know, you can't have the left of your array be after your right. That means we're done with our loop and we haven't found our element. So we get the middle. So the middle is going to be the left plus the right minus the left divided by 2. Or I believe what you could just do is left plus right in parentheses and then divide by 2. Now, if the array at that index is equal to your target, so the middle, so this would be the middle that we just found, is equal to the target, then we return that middle. We found our, return.
It returns the index.
It returns the index. So this returns the index of where our target is, not the actual value. Well, yeah, because you're looking for the value, you wouldn't want to return the value. It returns the index of where it is. So this returns the index of where our target was. Now otherwise, if it wasn't our target, then we would go into these two statements. So if our array, or where our index is, was less than our target, it means that our target is greater than it's greater than where we're at, so we have to go to the right of the array. How we do that is by setting the left to equal the middle plus 1. Because remember, this is in a loop, so every time this loops around, it's going to calculate a new middle based on left and right. And what you're doing here is by setting the left to being the middle plus the index of the middle plus 1, it will make it so that when you're looking and calculating this, it completely ignores everything that's the middle and before it. So otherwise, you'll make the right the middle minus 1. So if you're trying to look to the left. And then it'll keep looping around until it found your value. And if it did it, it's going to return the index of it. And if it doesn't, left will become greater than right, and then it'll return -1, which represents the target not being found. Anyone have questions with this code? Okay. Yeah, that was pretty short. So I don't think we put any questions in for binary search. But the next thing we're going to go over is tries. Oh, yeah.
What would a question typically look like for binary search if there was to have?
Fill in the blank. They give you like half the code and you fill in the blanks.
Okay. So next, we're going over tries. So let me first explain what a try is. Out of show of hands, how many of you know what a try is? Okay. It seems like that was went over in CS1. How many of you are comfortable with tries? Oh wow. Okay. So a try is just a collection of strings that are formed in a type of tree structure. So essentially, when you're putting in a string, it would kind of start letter by letter and go down making nodes. And then if you want to find a word so it's like a dictionary of words, but you can find a word much faster than if you were using something like a tree. And I'll explain why in just a moment. Let's move on. If I get confused, I'll let you know. Yeah. So can't we just store strings into a binary tree? So if we store strings into a binary tree, what happens? This is, I think, if any of you use like C++ or something, it would be like calling a set of strings, because that's built upon trees. So you would put in a string into like one of the nodes, and then you'd like lexicographically compare them to put them into other nodes. And this works just fine. Like for example, let's say you had the letter A, right? The letter A has it's 0 in the alphabet, right? It's the first letter. And let's say you put in B, right? It would go to the right of A because B is bigger than A. And it kind of uses this logic to build a tree. But that would be, like, you do this with entire strings and you do comparisons like that. And this forms into like an n log n behavior. And the reason it's not logarithmic is because to actually search a string and do comparisons, you have to do an O of n search, because you have to compare letter by letter by letter until you find the actual comparison, which string is bigger than the other. So I think this slide says that here. So string functions are expensive. So strlen and strcmp, length and compare, take O of n to process and find their results. So if we were to store these strings into a binary search tree, then each time we look and do a comparison between what we're looking for and what's inside the node, it would take O of n, and then finding the string on average would be log n. So for each node we look at, that's O of n, and then we have to do that log n times. So n times log n. So that's why it's disadvantageous to use a BST and why we have tries. So instead of putting in full strings into nodes, what tries do is they do it letter by letter. So let's say you have a string that says cat, so CAT. What it would do is start at the root, and it has a node of, let's say, the alphabet, size of the alphabet, so A through Z. And let's say you put in the word seal, like in here. You would go to the node in the at the letter S, and you'd say that, I think you turn on that bit inside the node structure. Do we have a code example here?
I don't know.
Yeah, I don't think we have a code example here, but we'll go over them in the problems. So you turn on a bit for just indicating that you have the letter S here, and inside that node it also has a typical structure asking if it's a word. So usually when you end something, so when you finish inserting a word, you would turn on that boolean is word in there and say it's true, this is a word. But everything else, it would just be on to indicate that you can go in this direction, that there is a word if you head here. So if we're inserting seal, we'd put S, and then this is like its own try. So it also has that node alphabet, and you'd put an E, A, L, and then at the end of that, you would say that over here it's a word. And then let's say you put in the word C. So now this saves memory, because when you put in the word C, you don't have to add in S and E again. But now you add in another node, E, because the letters differentiate here. And that's why a try could be useful, essentially for those memory reasons.
I'm going to interject.
Yeah.
The reason why we keep that bit to say whether or not that node is a word or not, imagine we entered the word sea like the ocean, S-E-A, right? In the seal example that's already down there, we wouldn't have to add any nodes, right? Because S, E, and A are already in the trie. Instead, we would increment that bit or that integer to say, hey, there's actually a word at this A in that position, SEA, right? Because if we didn't have that, we would have no way to determine whether or not C existed as a part of seal. So that's how we tries kind of have that memory efficiency, because we can store multiple different words in almost the exact same nodes. The only difference is that integer is saying, hey, this is actually a word. This is like a terminating character of a word. So that's one of the really good optimizations of tries.
Yeah, just as Dylan said. Okay, so what sort of operations do you have on tries? You can do an insertion or a search. So when you insert, as I just described, you would grab some word and you'd put in the letters one by one going through that node of alphabets. So for example, the letter C would be in the third position, and you'd go into that node, and then you'd start putting in the next letter in. So you make that node, you put it into the third position, and then you start doing the same process for all the next letters. So the letter A, the letter T. What word was I putting in again? Cat? Yeah. I'm very forgetful. So then searching would be practically the same thing but easier, because you're not actually putting stuff in. So now you just follow the line of nodes that you made. So essentially, let's say you're searching for the word cat. Let's say all the nodes are, I feel like I should draw this. That would be a much smarter idea than trying to explain it with words. So let's say we have the root node. Let's just call it root. Yeah. And we put in the word cat. So C-A-T. I feel like this is just to spite my handwriting, honestly. Why did I take this section? Okay. Well, let's put in another word that maybe starts with the letter C. Can anyone give me a word?
Car.
Car? Okay. So this is a good one. So we'd go down into C, then to A, and then we'd make a new node at R. And this is a word. I'm just going to mark it with a tick here. So a tick represents a word. Let's get 5 words in here. So 3 more words. Can someone recommend anything? Yeah. Okay. My spelling's not the best, so I don't want to embarrass myself here by misspelling. Cats. Okay, so cats would just go here, 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 and then it'd add a node S. And then this would get a tick because that's a word. 2 more words?
Leo.
Okay.
Okay.
So L, E, and then O. And then 1 more word, preferably starting with an L or a C.
Caps. C-A-P.
C-A-P, yeah. So we go to C-A, and then we make a node P. Okay, so that's insertion. That's how insertion works here. What about searching? So this is also gets a tick because it's a word. So does this. So now let's say we wanted to search for the word cat. So we start at the root, and we would look in here and see our next letter is C. Do we see C in here? Yes, it's a valid node. We jump here. Okay, the next letter is A. It's a valid node. We jump here. Okay, the next letter is T. It's a valid node. We jump here. We finish searching. This T at this node, is it a word? So this tick represents, that I wrote here, represents that we marked it as a word previously, like with the Boolean that was inside that node as data. So now we know that the word cat is in our trie. But let's say we're trying to search for a word that's not in our trie. Maybe Leon. So let's say there was an N here. Or there was no N here, but we're searching for Leon. So we would go down to the L, the E, the O, and then we would look for a node that's starting at N, and we don't see it. So now we know that the word Leon is not in our trie. And then to showcase one more example of deletion, searching. So to showcase one more example of searching, we can go and look for maybe L-E, yeah. So the word Lee, just L-E. So we would look at L, E, and we found we traversed all our letters, but the E does not have the tick. We did not mark it as a word. So we know that word is not in our try, even though we just looked through all the nodes. Any questions there with searching and insertion for tries? Okay. So, all right, let's get into the problems. So try 1, try 2. So let me maneuver to this on the iPad. So this is asking us to write an iterative, non-recursive function that takes the root of our try and a string str and returns the number of new nodes we would have to add to our try in order to insert that string. Okay, I think I just read that without understanding what that meant. So we write a function that takes a root of a try, a string, and it returns the number of nodes we would have to add to our try in order to insert that string. Okay, so essentially, if the try already had some number of nodes, and or some sort of words inserted, and we were inserting a new word, for example, it may already have all those nodes in there for that word. So maybe it has cats inside there, but we're trying to insert the word cat. Now, we have all the nodes for cat, so we're not actually adding new nodes. We just go down the try, and when we see the letter T at that last node, we would just set it as a word, and we're not actually adding any new nodes. So that's what it's asking us to do. You may assume that I just covered like a lot of the text with this. You may assume that str is non-null, non-empty, and contains lowercase alphabetic characters only. It won't contain uppercase letters or non-alphabetic characters. However, you must handle the case where root is null. So they tell us to handle the case where root is null. So they give us some special restrictions. Please do not use pointer arithmetic, probably to spare the TAs grading this. Do not modify or corrupt the try or the string. Do not add nodes to the try. Oh, so we don't want to actually add those nodes. So if we're trying, this is not an insertion. This is just the count of how many nodes we would have to add. Do not call strlen repeatedly, as it is an OK function. An O of k function, where k is the length of the string. If you need to call strlen, find a way to do it only once for the given string. So what that is saying is that just if you need to call strlen, just make a variable for it, because it's a helpful function. You don't want to find the length of the string using your own code. That would be a bit more writing than you'd want. But they're asking you to not repeatedly call strlen. So for example, calling strlen inside a loop, because it doesn't immediately find the size of the string. It has to loop through it. So we need to make it a variable if we use it. So what do they give us here? The try node struct and function signature are as follows. Do not write any helper functions. So we have our structure of a try node. So this is what I was talking about when I was explaining it. It has another try node inside of it, a pointer to a try node array that's called children of 26, representing all the letters in the alphabet, and then a flag, which represents if the string is in our try or not. So if it's a word. Yeah. So what can we start with here? So we have our string here, and then our root. What we could do is we can start by finding the length of our string, since that's going to be important. We're going to have to traverse through this. So they told us to not call strlen repeatedly. So we're going to want to call or find the length of our string. I should zoom in a bit. So int len is equal to strlen of str. So now we have the length of our string as in len, and we don't have to call strlen a bunch of times. So that's what this restriction was. Next, we're gonna want to start looking through our try and find how much nodes we can see so far. So we look through the length of our string, forint I is equal to 0, I is less than len, and we're looking through the length of our string because if we could go through this, because we're looking through each letter, we need to find the letters. So for example, let's say the string was, I don't want to say cat, I've said that too many times. For an example, let's say it was Dylan. Dylan was the string. That's a hard quote. Okay. So it would have 5 letters, so len would be 5, and we'd have to look through each letter and see if it's in our try and kind of traverse our try this way. So we look at the letter D at index 0, then Y, then L, then A, then N. That's why we're looping through the length of the string and not through a try. We can't loop through the try like that. This loop is kind of facilitating us going through the try. Oh my god. My worst nightmare, curly braces. So next, we have to check if our current try root is null somehow. So they told us here somewhere that, yeah, handle the case where the root is null. So if the root is null, we just have to add in like the length of our string. So we could say that the root is, we're constantly going to be changing the root since we don't actually need to traverse backwards or doing anything like that. We're not doing recursion either because they explicitly told us not to. Did they?
Yeah, they told iterative. Yeah. It's at the top.
Oh yeah, it's at the top. Iterative, non-recursive solution. So now if we're searching through this, we could say, okay, if the root is null, because obviously, not obviously, but if the root is null, then we can't actually look at anything inside the root. Then what do we want to do? So if the root is null, what do we do inside this loop? Anyone have any ideas? Yeah. Yes, we can break it, but we could also do something else. Yes, exactly. So I kind of represents where we are in the letters, and since we want to find how many nodes we have to add, the moment root turns null is also the moment where we have to start adding nodes. So I represents how much nodes or how much letters we went through so far, and if we went through like no letters, if I stays at 0, then we have to put in all the new nodes. For example, for the string Dylan, we would have to put in 5 new nodes because root has nothing in it, or it doesn't have the letter D in it. So we could just return len minus I. So what do we do next? Any ideas? Traverse? Yeah. So any idea how we would traverse through there? Or yeah, that's perfect. So we'd go ahead and say that we would set the root equal to root at children at str at I minus string A. So if you don't know what this minus string A does, the lowercase letter a corresponds to something like the ASCII value 97, I think. And if you do, you could just do subtraction between characters like this, and it'll automatically give you the index of. So like the letter A could be the letter A, or it could be whatever's ASCII value it is. So we know that the string only contains lowercase letters. So for example, something like B minus A would be 1. So that's what that's doing right there. And now what's happening is the root is moving forward and traversing forward. And then the next iteration that we go up here, we go to the next letter and see if the root is null, then we return the number of nodes we have to make still. And we kind of keep going. So we could end that. And let's say we traverse this entire loop or traverse this entire string, and we never returned here. The root was never null. It was never set to null. We had all the nodes already. What do we want to return at the end? Yeah. So at the end, we would return 0, and then we'd be good. So any questions about this? Yeah.
Would it like not cause an error if you got to the null character for the root equals the traversal thing?
This represents, so the array is filled with null elements, right? So when we look inside this array, so we find the index that we have to look at, 0 to 0 to 25, and when we select something in there, if it's null, it's just going to be set to root, and because root is a pointer, it could be set to null.
But if I got to the null character in string, oh, I guess it wouldn't. Never mind.
Yeah, because we only look through.
String length doesn't include the null terminators.
Yeah.
So we were iterating over string length, and string length doesn't return the length including the null. So we would never actually traverse the string to that point. If we did I was less than or equal to length, then we would hit the null terminator at the end, because we're not counting. Yeah.
Thank you.
Yep.
Yeah. So any more questions about this one? All right.
Oh, question. So.
Can you explain the in brackets versus like string of I minus n?
Minus A.
You could imagine like.
Sorry, my handwriting.
So the array, right? We're storing 26 pointers to another trie, right? 0 to 26, but the A character is represented as 97. So if we tried indexing that 26 long array at 97, we would get out of bounds, right? So how are we going to take that number and move it so that A is at 0, B is at 1, C is at 2, so on and so forth? If you subtract A, imagine, because A minus A is 0. They're the same thing.
Just do minus A.
And then, yeah, so B minus A would be 1, C minus A would be 2. So basically we're shifting the range over, because every character in C could actually be represented as an integer, is what its ASCII value is. So by subtracting A, we're shifting it so that it starts at 0. We're 0 indexing the alphabet, so that we can use that in the struct right there. At the top, we declare 26 children indexes, and so that we could use that. Does that make sense?
Yes, it'll
Alright.
just be like minus.
We're shifting the index over. It'll always be minus A. Yep. And lowercase a, because their lower and uppercase letters do have different ASCII values, and they say explicitly here that it will be lowercase letters. They said it was all uppercase letters, what would be subtracting by? Capital A, because we're trying to shift it to the start. Yep.
Yeah, if you guys want to take a look at the 1%, oh my god,
It's
wait,
been doing that. Make
Is-
sure it's plugged in. It's plugged in. It's
okay,
fine.
that's concerning. Is it,
It's fine. It was doing that with me. No,
okay, but it said 11%, no?
just going.
Okay,
I'll get mine just in case.
so, yeah, that's about it. Let's move on to the solution. So just as we wrote out, we could see that we're getting the length of the string, then we loop through len, and the length of the string, and if root is null, then we return len minus I. Otherwise, we go through root we traverse to the next node that we have to look at in the trie. And if there is no such node, it's gonna start going through the loop again, and root is gonna be null because we just set it to null if there was no node that we could go to, and then it's gonna return len minus I, representing how much characters we have to add, or how many nodes we have to add so far. I thought this was a calculator. Okay, so let's move on to the next question. I'm not sure why, but I think part B is an AVL question, but the part A is a try question.
So remember on section B of the exam, I said you could either get a try or an ABL. Well, I guess sometimes they give you both. So in this case, they gave you both.
Would you guys want me to do the AVL part as well, or just the try part? You want me to do the AVL part? Okay, cool. So first, let's go through the try question. So suppose we insert the following strings into an initially empty try. How many nodes would the try? How many nodes will the resulting try contain? Please count carefully, as credit for this question may be all or nothing. So maybe no partial. That's concerning, but yeah, they're telling us to count carefully. So one thing that immediately comes to mind here is, does the root count? Because if you remember in all the descriptions or all the tries that I've shown before, does the root count as one of the nodes? Yes. So the root is a node. So it does count. So that's kind of the trick part of this. But after that, it's really easy. It's all about insertion. Yes.
I spent 2 questions earlier today.
Yeah.
And if you get correct guess the correct amount of nodes without the node being a node, so like added 1, so you're off by 1, you get 4 points out of 5.
Oh, really?
Yeah.
I
Okay.
guess there is partial. I think they were lying.
Maybe you could just guess a random number and pray.
It's off by 1.
All right, let me guess. So 50. Okay, I'm wrong. All right, let me actually do the try. So first we start with the root node. What? That is not type of on this is being a little glitchy. Okay. That's so weird. Okay, wait. Technical difficulties, 1 second. So, root node. Yeah, it's drawing before I touch the tablet. Right, this is the root node. Okay. Ignore whatever that says. Just imagine it says root. So we start with the word cat. We would, yeah, it's drawing before, that's so odd. Okay, whatever, I'll just deal with it. So we make a new node C, then another one A. Oh my god. It's drawing before my pen hits the hits the tablet, which is really annoying. Sorry. So we're inserting cat, then we insert the letter T, and that's that word inserted. So how many nodes do we currently have? 4, yeah. So then we insert cap, so that goes to the letter C, then the letter A, and then we make a new letter here. Why did it start doing that?
I don't know.
That's so odd. Yeah, just imagine these are comprehensible letters. So now we have 5 nodes. So then we want to add the word catapult. So we go to C, to A, to T. Then we have to add more from T. So A, P, what the? Oh my god. P, U, I, do you wanna try writing?
Okay.
That's
Apparently we have technical issues here. Catapult. Would you just insert?
I didn't finish inserting it. I
C-A-T-A-P-U-L-T. Oh, I see what's going on. Okay. Well, we're gonna thug through this. Catapult, catalyst. So C-A-T-A-L-Y-S-T. Sort of writing the nodes. Phosphorescent. We don't have anything from here, so you have to do this whole word. Okay, this is really bad actually. I don't know what's happening with my tablet up here. Phosphorescent. All right. Another way you could do this problem instead of writing out the entire thing here. I'm gonna try fixing this. I feel like my pen might be low. Yeah, go for it.
Okay. Yeah, so instead of actually going through and doing the entire try, you could kind of just write the letters out as Dylan has been writing. So you could write, you could see cat that has CA, and then T. So we have the root, so that's okay.
My pen's on 1%. That makes more sense. Explain.
Okay. Yeah, so you could go ahead and write all the words out, and then you could kind of just go and follow the try structure. Oh. Okay, well, we got an answer.
I'm going to move on to the next segue so that this thing has some time to charge. But essentially, the way that you could also do this problem is writing like this on a left to right type of manner. The root counts as 1. Don't imagine root as a word. It isn't a word. But if you put cat, C, A, and T have never been introduced to the try before. So that's 3 that you're adding. On top of that, cap, we have the C and the A from the cat above us, but we're inserting the P, so we're only counting 1. And if you look at the right-hand side, we're counting 1. Same thing for catapult. We already have the C, A, and T from before, so we just add apult, which is 5. Same with catalyst. Phosphorescent, there is no P ever introduced in this try, so we can add the entire length of the word, 14. Pancake, we only have 1 letter, the P. The rest is new. And then pancakes is just going to add 1 letter. It's actually going to get us 35. So 5 points for a correct answer, 4 for answering 34,
There's a question.
or for answering 36, right? You see the 1 off. Question.
Would we ever be given a question, like a question on the foundation exam where it's like you have to draw out the whole try and you're given words?
Yep.
Yeah.
Some of them, they explicitly say draw it out. So if they say draw it out, you better draw it out. But in this case, they only want the number, and to save all of the heartache of watching us scribble nonsense, this is another way you can do it. Hopefully, my pen's charged enough with like that 2 minutes. I have a very strong power brick. Let's try to do the AVL problem now.
You want me to take over?
No, I got the AVL. All right. Oh. Who missed the ABC method? It's coming back. All right. So, we're going to insert 42. Where's 42 going to go in this case? Left of 59. So 42 goes down here. I'm in gesture mode. 42, right? And so we now have an issue here. The right-hand side of 38 is a height of 2. These 2 elements right there. And its left side has a height of 0. So 38 is the one that triggers our rebalance, right? Does everyone see how 38 is the trigger? Because its right side is 2 bigger than its left side, the height. So that's the issue here, right? So our first node that we grab is going to be 38. What's our other 2 nodes? 59 and 42. So we have A, B, C. So which one's going to be which? We have 38, 59, and 42. So 38 is the smallest. It's going to A. 42 is the middle element. It's going to B. 59 is the largest. It goes to C. And that's going to end up being, we remember how that looks, A, B, C, right? So that's going to be 38, 42, 59. And then we reattach that to where the first parent used to be. So the outcome of this is going to look like 18. It's going to attach to this tree we just drew to the right. 42, 38, 59. And then reattach everything as it was. 7, 12. So now in this case, do we have any balance factor issues here? Everyone's good. This guy has a balance of 0. Also has a balance of 0. Balance of -1. We're all set. Everyone good there? 5 points for that. That's a pretty simple AVL problem. Pretty straightforward on that one. All right, we're going to move on to heaps. Give the pen some time to charge before we get to practice problems. And yeah, hopefully that issue doesn't persist when we get to the heap section.
Okay.
Oh my God.
take back over for my last section here. So heaps. Let's start that. Okay, so there are two types of important heaps that come up on the foundation exam, and it's the min heap and the max heap. So the min heap is a heap that starts with the smallest elements, and as you go down, it has larger and larger elements. A max heap, it starts with the larger elements, and as you go down, the elements get smaller and smaller and smaller. So the heap is kind of it's a tree structure, but usually the best way of implementing it is using array. So I'll explain that in just a moment. How many of you, so I don't know how many of you have heard this, what a priority queue is, but a priority queue is it's a type of data structure inside of a language, inside languages that you could just import and use, and that's based off a heap. So heaps are very useful for just putting things in and then being able to find like some element that you need that's at the minimum or the maximum, and they're really easy to kind of implement using an array. There's also something called a heap sort, which I'll go over in just a moment. So heap operations, what can you do with a heap? So you could place the value in the first open child spot going from left to right. I'm going to show this in just a moment after we get to the next slide. But essentially, we could say that our tree is always going to be balanced because when we have it as array based, we will just, when we're adding in an element, we will always add it to the end of the array. And the end of the array kind of represents the bottom right of the tree. Let me see if I can, pen's still charging. You'll just have to bear with my explanation for now. But essentially, it's just a tree that goes from the top, and then you start with the root, and then you start with the left of the root, and then you go right, and then you start at the next level of the tree. So you fill in each level of the tree, and when you're done filling in a level, it goes to the next level, and it kind of keeps going. So you fill it in from left to right, and that's how it works array based. So when you insert, you put it on the very bottom right of the tree, on the next open level, and then you look at its parent, and if you're doing, let's say, a min heap, right, the minimum elements have to be at the top and the larger elements have to be at the bottom. So let's say you put in the number 1 inside of a min heap. Then you look at its parent, and if the parent is greater than 1, or whatever element you put in, then you swap, and you keep doing that until you reach the top, or until you reach an element that's smaller than it. For max heap, it's the opposite. You would look for, since you want elements that are bigger at the top and smaller at the bottom, you would go ahead and find its parent, and if the parent was less than the element you inserted, you would swap. So that's kind of the differential between min and max heap. And to make a heap, there's a function called heapify, which they will ask about on the exam if you get a question like that. And heapify essentially just does a bunch of insertions into an array from like let's just say you have an array of elements, and this array has nothing to do with heaps. It's just a plain array. But then you have another array in a heap structure, and then functions that you use with the heap to do insertions. So you would take every element from that plain array and insert it into the heap. And you may be wondering, okay, well, we have n elements, and we put it into the heap with insertion until we have a full heap. So n elements and an insertion is log n. Why is this O of n, right? So actually, since we're inserting the next element at the bottom left or at the very bottom layer, the worst case of insertion is log n, because obviously, let's say it climbs all the way up the heap and swaps with every element, and that takes log time, because the heap is always a perfect balanced tree. However, on average, it will be O of 1. And the reason for this is because let's say you're inserting a bunch of values into the heap. Each level of the heap that you go down, since it's a tree, let's say the first level has 1, the next level has 2, the next level has 4, so on 8, 16, 32. So there are way more elements in the heap at the very bottom, and then as you go up, there's less and less elements. So when you put an element in, to go all the way up, let's say in a min heap, it would have to be the smallest element inside the entire heap. So let's say there is like a giant heap and you have to put in the value 1 to make it go all the way up. And essentially, because of the structure, at the very bottom, let's say we had 32 elements. Up top we have 16, then we have 8, then we have 4, 2, and 1. We have the smallest numbers, the 32 smallest numbers at the very bottom level, I believe, right? So we have the 32 smallest numbers at the very bottom level, and because of this, if we try to go up a level, that means the number we're inserting next is going to be greater than half of the numbers that are already inserted in the heap. And because of this like probability, it's called like an amortized runtime of O of 1, because each time it goes up, there's a smaller and smaller probability that it would go up again, because all the numbers constantly increase and increase, or decrease and decrease, depending on min and max heap. That was a bit of a rough draft explanation, so any questions on that? I think the pen should be working soon too. What's up? Okay. Oh, there was supposed to be text here. Hold on. There is my slides that I put in my updated here. Yeah, give us a moment.
There you go.
We're gonna have to go all the way back.
Where are we? Okay, we're on binary trees. Okay, we're on day 3, Bitwise. Okay, we're almost there. There you go.
Okay, cool. So, array-based heaps. So in a one-based index system, so that means, let's say you imagine the first element in your array to be at index 1. To traverse a heap like this, let's say you were making this this heap, right? Or let's just look at this heap for the moment. So 1 would be the top, the root, and then we'd start by going left to right on the next level. So we'd place elements here and then here. And then let's say we were inserting something new, it would go as a new node to the right of the 6. And then so on, we would go levels left to right, left to right. So we could see here that the first indexed element is 1, the next one is 3, 6, 5, 9, 8. And if we inserted something else, it would be a new element or a new node. So to traverse this array, what we could do is just use logic like this. So to go to the parent of wherever you are in this like array that's representing a tree, you would just take the index you're at and divide by 2. And because of integer division, this should also work well enough. And remember, this is with a 1-based index system. If you're using a 0-based index system, there is the formula changes up a little bit. But on the FE, I know that they like to use the 1-based. So even if you don't know the formula by heart, you could just kind of write out an array and see, oh, let me mess around with this. It should be like something similar to this. And you could find, oh, I could go to the parent by using this, or I could go to the right or left child using this. It's pretty similar. With a 0-based index system, it's like IDEX minus 1 divided by 2. So it's a very small change. But what this does is, imagine since each level in this tree doubles the next level you go to, this division by 2 kind of jumps back a level. That's what it means. So let's say we were at 5. So in a 1-based index system, this would be index 4. And let's say we divide by 2. 4 divided by 2 would go to 3, right? So 5 is right here, 3 is its parent. Let's say 9 is index 5, right? 5 divided by 2 integer division is also 2, so it would go to 3. So 9 and its parent is 3. So that's kind of how that works. To go to the left child, we go 2 times index, and to go to the right child, we go 2 times index plus 1. So we could see right here that going to the left would be, let's say 3 is index 2, right? We have 3 at index 2, and 5 and 9 at index 4 and 5. So 2, its index in here, times 2 would bring us to 4. 2 times 2 plus 1 would bring us to 9, index-wise. Anyone have any questions? Okay. Yeah, so this is how you would traverse an array-based heap. So time complexities. So I think I went over this already in my previous slide, but the time complexities, I did see a question on a practice exam before where they just, was that on our exam? They specifically asked like,
exam. They just rapid fired runtime questions for heaps.
yeah, so they asked us like every single runtime for a heap. So what's the average, what's the worst, what's the best case for a heap? Now these show average cases except for insert. But I could explain the best case and worst case. So for find min, it's always going to be O of 1 because finding the min is just looking at the top element inside the heap. And what that means is, oh, I didn't explain deletion. Whoa, I did. I didn't explain deletion. That's my bad. Hold on, let me do that before I move on. So how you delete is, if you remember, I was kind of explaining how you would do an insertion. You would add something in here, and let's say we added the element 0. We would look at its parent, and if its parent is less than 0, because this is a min heap, see the smallest elements at the top, or its parent is greater than 0, so we swap 0 in this, and then 0 would then compare to 1. 0 is less than 1, so then we would swap, and kind of go back here. But let's say we want to delete. We only delete the top element ever. I think that's the only use case where we kind of do that for a heap. We can delete other elements, but there's really no point because the use case for the heap is to find kind of the minimum element or the maximum element. And we know that the minimum element is going to be the root. So we have to do root deletion. And how we do that is what we do is we just swap the root with the last value. So the last value is always going to be somewhere to the right here, just like as an insertion. If we were inserting it here, it's 8. So we swap 1 and 8. We delete 1 because we could do that now. And then what we do is we would just move this down. So this, let me grab the pen, maybe it'll work. Still on the wrong. Okay.
Doesn't have the updated slides on that.
Oh, it doesn't have the updated slides. That sucks. Okay, wait. We could just use this one. I know it's a little blurry, but we're improvising. Can the pen write while being charged?
I don't think so.
Alright. Okay, so let's say we were inserting 0 into here. We would put in 0. Okay, that's like a dot, but it's a 0. Trust me. This is a max heap. We see that all the elements that are below 11 are smaller than it. So actually, let's put in a larger value. Let's put in 12. So we put in 12, and we would look at its parent, which is 9. And since it's a max heap, 9 is less than 12, we would go ahead and swap them. So now, 9, this becomes 12, this becomes 9. I'm showing insertion right now. And then we go ahead and, oh, that is, yeah. I clicked on a different, oh, where am I? I'm lost. Okay. Oh no. Okay.
Use the slider at the bottom. Slider
Yeah.
at the bottom.
It's gone. Okay, wait. There it is. We get a lot of slides. Oh, this is sorting.
Pass.
Yeah.
Nope. Keep going. Keep going. Keep going.
There it is. Okay. We made it back. So you get the point. It would kind of just percolate upward. That's what the name of that is, percolating upward. So it's swapping up until it can't swap anymore, or its parent is either smaller or greater than it based on max and min heap. Now deletion, let's say we were going to delete this 11. We swap it with the last value in the array, which would be this. Remember, it's an array-based thing. So this would become 8. This would become 11. We get rid of 11 because we don't like 11 anymore. And then we percolate 8 downward. So we check for the bigger, since it's a max heap, we check for the bigger element of the 2 below it, and we do a swap. So 10 or 9, which one's bigger? It's 10. So we swap with 10. Then this only has a left element, so we look at that, and 8 is bigger than 5, so we keep it like this. What's up? Yeah. So that would be kind of our heap, our final heap after a deletion. So, and it's still keeping a balanced structure. If we were inserting next, we would insert like here, let's say in the value 4 maybe. Okay. Let me go back to the slides. Okay, that was deletion explained. So because insertion, I was explaining how it has the average case of O of 1 because of the one amortized rule of having half the values that are the smallest be at the bottom, and so on and so on. So it's unlikely that it goes up further and further and further the more it goes and swaps. But deletion does not have this value, or does not have this sort of average case. And the reason for that is because of that swap we do. We swap with one of the bottom elements. So it has a very high possibility of just going all the way down. So an average case, deleting the minimum or deleting the maximum would be log of n. Best case for deleting the minimum would be O of 1. The reason for that is imagine just a heap with one element. We don't have to actually do much. So finding the min is always O of 1. Insertion, worst case log n. Best case and average case O of 1. Deleting min, best case O of 1, average and worst case log n. And finding min all across O of 1 because we're just looking at the root. Yeah. And I already explained the average case of insert and then heapify, which is making a heap from an array. Okay, here's just an example of the heap. I was planning to use this to draw stuff or explain it, but I already did. Heap sort. This is just calling the heapify function. That's it. So heapify makes the heap in O of n, and then you could just call you could call deletion and grab the root value, and then the next value would become, what's it called? The next value would become the next smallest or next largest based on max and min heap. And you could kind of keep taking values out and out and out until you get all the values in a sorted order. And even though amortized, or heapify is O of n, because you actually have to take all the values out to read them first, taking each value out is O of log n. So taking out all the values from that heap and having them like maybe in an array so it's more accessible would be O of n log n. So to take out each value, it's logarithmic, and to actually make the heap, it would be O of n, and it results in an O of n log n complexity. Any questions about heap sort? Okay. So let's get to these problems, and then I'll pass it off to Dylan. So this one has a bit of stuff on here. Let's see. Right here, we could see that they're utilizing array-based heaps, which will probably be utilized the entire. Hold on. We don't have the heap questions on the iPad.
They're not there?
Yeah. Okay. 1 second.
They're not gonna be here.
Can we restart it right now? Yeah. Give us maybe
Explaining while I do that. We're long.
3 minutes. Yeah. Okay. So let's see what this says here. I'll read through it. So we have a heap. It says a heap is represented by the array below. The first item is stored at index 1. Answer the following questions. Please answer the data, not the index where it's stored. So who is the left child of 13? So if you remember the formulas for indexing of 1, we could just imagine that this tree, yeah. Let's see where 13 is. 13 is at index 3. So the left child of 13 would be just times 2. So times 2 would be 6. So the left child of 13 is 19. What about the right child of 16? Any ideas? Yeah. So 4 times 2 plus 1, we would go to 9. So the right child of 16 would be 20. And what about the parent of 24? Yeah. So 7 divided by 2, and then it integer divides to 3. So we would go to index 3. So the parent of 24 is 3, or the parent of 24 is 13. But, and vice versa, 24 is the right child of 13. Okay. That's the first part there. That's 3 points. So consider the following tree. Is this a valid min heap? Justify your answer. Just saying yes or no has no credit without justification. So they want you to explain a bit. So this is kind of hard to see, but this is an 11. This is 21. This is 31. This is 51, 41, 65, 48, 71, 90, 101. So it looks like all the values are going downward, right? But is this a valid heap? No. Why not?
Shape property.
Yeah. So it's shaped improperly. So you could see that if we go down level by level. Wait. I think it's just drawn badly. Hold on. Let me.
No, there's a gap right here.
Is there?
Yeah, right there. It's not complete.
Oh. Okay. Yeah, this node doesn't have children, so it's not valid. It has to go from left to right. All right, we got our tablet back up. Okay. So we could see that over here, there's no children here where there should be, because it has to go left to right when doing insertions. So this is not a valid heap, and you could say no, it's not a valid heap because 41 does not have any children, and it has to have a proper shape of a left to right property or a balanced tree, a tree that goes from left to right, balanced. Bless you. Okay. So that's another 2 points, so that's 5 points right there. And then let's look at this question right here. So what do we have here? Consider a min heap stored in an integer array, heap array of 100, which is globally declared. Complete the percolate up function below that takes an index and perform the full percolate up operation for the item at that index. While writing the code, you can assume there is a swap function available for you that is described below. So what they want us to do is write that one swapping function after you do insertion. So you could imagine you insert, and then remember you have to look at its parent and go up. That's what they want us to write, percolate up. So it's fill in the blank, so it's much easier than just writing code. But right here we have a if something is greater than 1. That's something, it would be index. Because let's say, because it's 1-based index, they already told us that at the very top. This is part C. So if we were looking at the root element, which is at index 1, then we have nowhere to go. So index is greater than 1. And I think this only has to perform the swap once, because there's no while loop here. They don't tell us to do, they don't have a while loop, so we only do the swap once. So then, this giant if statement right here, we have to write something and then a swap happens. So we should only do a swap in a min heap if our parent element is greater than us. So we have, what do we get? We have heap array. They told us we have an array called heap array, and it's globally declared, so we could use that. So if we say that heap array at index, that's where we're at. Heap array at index is where our element is, so that's the value of what we just inserted, or where we're at. And that has to be smaller than heap array at what? Index divided by 2, yeah. I'm bad at writing. Index divided by 2. So this means that we need to percolate it up and we need to swap. So we would go ahead and grab the address of, see, the swap function takes in pointers, so we can't just put in heap array at some place. We have to do heap array at IDEX, and then heap array. Oh, it's recursive. I didn't see that. Array at IDEX divided by 2. And this swaps them, and then we percolate up at IDEX divided by 2, because that's our new index. Any questions there? Yeah.
So you only percolate up when the inserted value is smaller than the parent, right?
In a min heap, yes.
Yeah, but
yeah.
we're working on a min heap, right?
Yeah.
Oh,
So
okay, yeah, never
yeah,
mind.
they'll tell you if you're working with a min or max heap, and depending on that, this may change. So if you're working in a max heap, it would be the opposite. We would only percolate up if our element was greater than its parent. Yeah. Okay. Any other questions? Yeah.
Why is there a and sign in front of the first heap array and swap?
I forgot that one. That's my bad. Was that your question? Yeah. Okay. Any other questions? All right. So we can see right here. Oh yeah, I didn't actually write out the values, but I think you remember what I said. So right of 13 is going to be, or left child of 13 is 19. Its index is 3 times 2. That's its left child, 19. Right child of 16 is 20. 16's index is 4. Right child is times 2 plus 1, 9, 20. Parent of 24 is 13. 24 has an index of 7. Divided by 2 with integer division, it's 13. It is not a valid bin heap because it's not a complete binary tree. That's what I was trying to get at the whole time. I just didn't know how to say that properly. So heaps have to be a complete binary tree. Specifically, 41 has no left child, but 65 has a child. So that's what makes it incomplete. And then here, while index is greater than 1, that's 1 point just for writing that. To make this gap in logic of the heap array at index divided by 2 is greater than heap array at index is 1 point. The addresses swap, 2 points, and then percolating up at index divided by 2. Okay. Next question for heaps. Let me move over on the tablet. Okay. So let's read this. A minimum heap is typically implemented with an array, with the root node minimum value being stored at index 1 of the array. To insert a new value into the heap, it's originally placed in the first open slot, followed by running a percolate up operation. Write a function that inserts a value into a heap in this manner. You may assume that the array is allocated to be big enough to store the newly inserted value. The function prototype is as follows. Insert, they give us the heap, the current size of the heap, and the new value we want to insert. Heap is a pointer to an array which is currently stores cur size, number of values, but has room for at least one more. New val is, so that's important. Let me highlight that real quick. So it stores the number of values, but it has room for at least one more. New val is the new number to be inserted into the heap. Write this function which inserts the value into, oh, I lost where I was reading. Inserts the value new val into the minimum heap. Take care to avoid infinite loops or array out of bounds issues. You may assume that index cur size plus 1 is in bounds for the array heap. Also, remember that index 0 of array heap is unused. Oh, so maybe they have index 0, but they just don't like it. Okay. Oh, wait. It's because if you're percolating upward, they probably want you to go to index 0, which has nothing. That makes sense. But yeah, that's why they're using index 1, I guess. So you may not write any helper functions. Okay. So what can we start with here? Heap, I think heap is a pointer to an array. So this is just an array called heap. Let's okay, it's just an array called heap. So first thing we do when we insert a value, what do? Any idea here? Yeah. Okay, that would be right, but they told us that we have at least one more. Yeah, yeah. So yeah, so put it at the end. So heap at cur size plus 1 is equal to new val. Okay. What next? So next, do we have a percolate up function? I don't think we do. Hold on. Yeah, so we just got to write that. So lucky for us, and I don't think these were on the same exam, and they wouldn't be, but we just wrote one. Because if you wrote this, then you would actually have the code for basically doing this too. So now you just have to make that gap in logic of going up from where you are currently, and then ending when your parent is no longer smaller, or no longer bigger than you, because it's a minimum heap. As long as your parent is larger than you, you swap, because the smallest element has to swap and go up to the top. Okay, so we could write a while loop. We also would want to write, so instead of, not only for easier writing purposes, but because we're looking at a current index in the heap, and if you remember from the last question, in the recursion we went and did index divided by 2, and we kind of had the new index we were at. So now we have to store the new index we're at every time we swap upward. So up here we're going to want to have a variable called index, and then currently we're at cur size plus 1. So then, while index is greater than 1, what we could do is then start percolating up if we can. So if our parent heap at index divided by 2 is greater than us, then we have to swap. Or wait, if it's greater than us, we have to swap. So we could write like that. So then, now to perform a swap, without the swap function, what we could just do is write temp is equal to where we are currently, and then where we are currently could be swapped with our parent, or the value where our parent is, and then where the parent is could be swapped with temp. And yeah, that should be it. There's also a return statement we have to do. Oh, never mind. Yeah, we don't have to do a return statement at the end. Oh, hold on. No. I'm missing one thing. Anybody know what I'm missing? Yeah.
You have to change IDX to IDX over 2.
Yeah. So after this, if we swap, we have to change the IDEX to go to our new IDEX, because now we have to do the while loop again, and we have to see if where we're at currently can go up again. Yeah. Any questions about this code? Okay. Yeah, so let me go over to the solution. So we could see we make the new value, put it in. Index is equal to current size plus 1. Then while the index is greater than 1, right here, instead of saying if it's greater, we go, they just break it if it's less. They break the loop. Oh, actually, yeah, I guess what I wrote is wrong, because if it's not greater than, okay, one sec. Here, wait. We're gonna go back to this, and instead of putting this inside the if statement, we'll just put it outside the if statement, and then it works the same way. Because sure, it doesn't, it's a less efficient insertion because it doesn't actually stop immediately when it says it can't, but it works this way. And you should still get full points. Yeah, let me move over. So they break the loop if the index, if its parent is less than the heap, where we are currently, the value where we are inserting currently, because then we wouldn't want to swap. Otherwise, we do the swap, and then we divide index divided by 2, or we divide index by 2, and we keep going through this loop. All right. Any questions there? Yeah.
With the way we did it, like just having an else statement for break, would it not be the same thing?
Yeah, it would.
Or we're still correctly?
Yeah. So if you just made an else statement for break, that would be fine. They don't care if as long as it works. That's what they care about. If we look at the partial right here, maybe they'll say something about efficiency, but I doubt it. 1 point for placing new value in the correct size. So that's right here. That's 1 point. Some loop or recursion. So they do a loop here. We did a loop too. Access array at current index divided by 2. That's another point. Triggering a swap if appropriate. Yep, swap mechanics and correctly ending the loop. Oh, I guess you did need the breaks. Oh, actually no. I guess they would they could give you the points because the loop would still end as long as it did an infinite loop. They explicitly said it in the problem statement too, so I'll avoid infinite looping, and I still did that. Well, I think this just means as long as the loop doesn't infinite loop. But yeah, breaking is easier to write and the better approach. Yeah, I'm gonna pass it off to Dylan for hashing and permutations, and then that is our entire FE prep series.
All right, let's bring it home. So, hashing and hash tables. Why do we care? Why do we use them? How do we use them, etc.? So the big reason we wanted to invent hash tables as a data structure is because accessing an array is actually called direct access memory. So when we take an array and we index at, say, 5, that retrieval operation in that array is instant. It's O of 1. Now, we really like O of 1 because that means, it's quick. And we like quick when we're writing programs because who likes waiting for anything these days? So hash tables are really, really cool. So how can we trick our data into sort of being in an array in a way that we can just one-trick access it from that array? So, for example, if we were to put, we could have an array of strings, and let's say we want to know the index of apple. How are we able to, we can't index an array with the word apple. That's just not something we can do. We could make an array of size however big, 9,000, and we could take the sum of each of the letters, and that's the index, right? Well, that's not memory efficient at all. We're holding on to all of these different values for no reason, and maybe apple has the same sum as zebra for whatever reason, right? So there's a lot of different issues that we have with just using a standard old array, and so that's where we introduce hash tables. So again, hash tables are all about exploiting the O of 1 constant time of accessing an array. And so the way that works is by putting a little middle layer between your data and the array that we're using. And that's called your hash function. Essentially, you pass in this case, apple or zebra, into a function that is going to output a number. That number is going to represent your index, right? And so now we have a way to, so here, for example, John Smith. So let's say we have an array full of phone numbers. And we pass John Smith through the hash function, and that's going to give us John Smith's phone number. So in the example of using John Smith as the index to the array, we get rid of that. We don't have to do that anymore. One, because it's not really possible. And two, it would be wasting space if we tried hacking it in some other way, right? So now we have this O of 1 access here. And the same thing works for Lisa Smith. If we want Lisa Smith's phone number, we pass in the string Lisa Smith to the hash function, and it's again going to return us a number. So that number can be bigger than the size of the array. We always want a modulus so that we loop it around, right? And so that's essentially the idea of a hash table, right? And that idea by itself is a great one, but obviously we run into a lot of issues with the concept of a hash table. Even though we're using a hash function, what if Lisa and John Smith give us the same hash value, right? So now we need to start thinking about what makes a good hash function. What do we do if there is a collision? And so that's a lot of the heavy lifting for hash tables, is not even understanding the hash table itself, but those sort of reconciliation strategies we have for when we hit those collisions. And so that's what almost all of your problems on the foundation exam are going to be about. Very few of them are actually about code or hashing. A lot of them will be tracing a hash table, figuring out those indexes, doing all of that modulus, all of that stuff, and knowing the difference conceptually between all of those different ways we can do it, right? And so just to talk about hash functions, the biggest thing that a hash function needs to be is deterministic. And by that I mean every time I pass in John Smith, I get the index 5. Every single time. If that were to change, then well, we just ruin the entire existence of our hash table. Our hash function is garbage and we used a random number somewhere, right? So the first thing, a hash function needs to be deterministic. The second, a hash function needs to be efficient. If we do a loop for a loop for a loop for a loop for every character inside of our array to make it really complex, we're adding runtime. So a good hash function is simple, it's quick, right? And then of course, distributed. And by that I mean, let's say we have an array of size 500. If half of the hash functions yield the index 1, that's a terrible hash function because we're going to keep getting collisions over and over and over again. So a good hash function wants a large range of numbers so that we minimize our amount of collisions, right? So that's what makes a good hash function. Any question about hash functions as of this point? Hash functions, hash tables, we're good? All right. So a lot of what we have to do with hash tables is dealing with collisions. And so what's a collision? I've been describing it many, many times. A collision is when two elements have the same exact index in the hash function. And we call that a collision because it's, imagine you're trying to put an item into a spot and there's already something there, it hits it, it collides, right? And so there are two different ways we can deal with collisions, and then those two ways have their own two ways. So there's four we need to consider. There's open hashing and closed hashing. So to describe what both of those are, for open hashing, this means we can store multiple things in a specific index. So imagine instead of a 1D array of John Smith, only one phone number, imagine each of those was another array, and we have a 2D array. And maybe each index can store, say, 10 phone numbers, right? That's an example of open hashing. It's basically saying, okay, we're open, we'll just make more room, right? So that's open hashing. There are two strategies for open hashing, which I'll go over in a sec. And the other one is closed hashing. This is where you say, screw you, this is my bucket, I'm staying here, go find somewhere else. And then we have a strategy of we need to go somewhere else, we need to find another index, and that position is closed. No matter what we do, it will not open up for anyone else. So those are the two different types, and you need to be able to explain those conceptually. So for open hashing, we have two solutions. We have bucketing and we have chaining. So bucketing is what I described just now. It's just a big 2D array where let's say, okay, let's be optimistic. We're only going to need 15 phone numbers. No way we have more than 15 different names colliding at the same time. The issue with that is it's the same thing as the difference between an array and a linked list. For bucketing, you set, okay, 15 times is how many phone numbers we want. And imagine they never ever collide. Imagine you have 50,000 people that never ever collide. You're now wasting 50,000 times 14 spaces in those arrays because they're never getting filled past that first element. So that's an issue. And so to solve that issue the same way we do normally, we do linked lists. So linked lists is called chaining. So instead of it being an array at each position, each index is a linked list. And we remember inserting at the head of the linked list is what? It's O of 1. So unless we're retrieving from the hash table very often, that's an okay approach. But again, that when we have the linked list get really long, when we search, we're going to have to do that O of n search through the linked list, right? And so like I said, this is chaining. It's memory efficient as opposed to bucketing, since we only allocate memory as needed. If the chain gets too long, though, we have an O of n search time. So again, that's why we need good hash functions. If it's not distributed and everybody keeps getting the same index, we're going to have a real long linked list, which means we're going to have a real long runtime, and we're going to lose all of the benefits of the hash table. So it also relies on a good function. Yep, essentially what I said. So now to talk about the two closed alternatives. And between these two, you only need to know the conceptual difference. But these you really need to know like how to actually do them, right? Because a lot of the hashing table problems are going to be tracing these two types of reconciliation methods, right? And so linear probing is, okay, let's say John Smith is at position 1, but Lisa's already there. So we check 1, okay, it's full. I'm going to check 2. That's it. And you keep doing that until you find a spot. So let's say 2 is full by Daniel Smith. And now we go to 3. And 3 is full by Leo Smith. Now we go to 4, right? So that's linear probing. We just keep going up by 1 until we find a spot. The other one is quadratic probing. So keep in mind that we keep checking in quadratic numbers. So let's say 1 is full with Lisa Smith. And so we go from 1 and then we go to 4. How did we make that jump? Because we went 1 squared to 2 squared. So we went to 4. If that's full, we go to 3 squared, which is 9. And if that doesn't work, we go where? 16. We go to 4 squared. And keep in mind, that's on top of the initial index where the collision happened. So let's say the collision happened at 5. What would our next index be? It would be 6, 1 squared. Let's say that were full. Where would it go after that? 5 plus 4, which is 9. That doesn't work. So then we do 5 plus 9, which is 14. And let's say that works, we're good. Right? So that's how you do quadratic probing. Okay? And so here's the example. 1 by 1 is linear. Quadratic is we keep jumping by those different powers, right? We keep doing that quadratic approach. And so usually quadratic is a lot better than linear because of the whole idea of distribution. Again, we don't want a lot of clustering, so we're throwing it even farther and hoping it ends up somewhere novel, right? It's more likely to find open spots in less populated arrays, but it's less likely to find open spots in very full arrays. So keep that relationship in mind because they'll ask you, when is a quadratic probe bad versus a linear probe and vice versa? A quadratic probe is not good in a mostly full hash table. Why is that? Because it has the chance of just infinitely going over the open square over and over and over again. But in a mostly open hash table, we just chuck it that way and it's probably going to be open, right? So linear is better in full arrays, mostly full hash tables. Quadratic's better in mostly empty. Cool? And you could probably even optimize this by saying, okay, we're going to keep track of the number of elements, and if it's 80% full, let's swap to linear, right? If you were writing this up in code. I don't think I've changed the title slide of the problems again for like the 4th time in a row. But let's go ahead and get started on our problems for hash tables. Before we get started on problems, any questions for hash tables? All good? All right, then let's get into it. So this is going to be a lot of what are the problems that we're going to see, and it's going to be very similar to the next one. I think this one's just a smidge easier, though. So we're going to basically take these values, and we're going to insert them. They've been kind enough to already give us the hash value, so we don't actually need to compute the hash value, right? And so they also gave us a table length of 10. Why is that nice and considerate? Because it's really easy to find the modulus of 10. You just take the last digit. And the reason I say that is there is no index. God, what number even is this? 1, 2, 3, 171 million. There is no index here, right? So what that has to do is it keeps wrapping around. And so the way that we would find this position is we would do this mod size, which in this case is 10, which is going to give us the position of 2. Do you guys see how I derive that? Good. All right. So let's insert this 1 by 1. And we have to keep in mind that we want a quadratic probing style, okay? So insert the following to the hash table. Tables that exceed 9 in this case. There's a standard note that there is a standard technique for dealing with hash values that exceed the length of the table, aka use modulus. They're saying remember when we taught you that, right? So for the first thing, wicked, we don't even need to bother with this. Wicked goes into position 9. That's not 9, that's 8. I'm stupid. All right. Cheesy goes in position what? 2. Cheesy's in 2. Lasagna, where's that go? 1. Lasagna. Okay, we're all good. 4, where is this going to go? So we go to position 9. 9 is taken. So let's try our quadratic probing strategy. What is the next index we go to? We go to 0 because we go 1 forward. And that means 4 now goes in position 0. So now the question is, we have dinner. And I think we can kind of see where this is going. Dinner goes where? 9, but it's taken. So we go to 9 plus 1, which is 4. That's taken. What's the next quadratic we need to go to? 9 plus 2 to the, it's 4. Because you go 1, 4, 9, 16. It's each of them squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, so on and so forth. So now we're going to 2 squared, which is 4. And here's room for dinner. Wait, no. 9 plus 4 is not... 9 plus 4 is going to give us 13 mod 10 equals 3. So dinner goes here. And so everyone kind of see how we did that. So we have wicked for lasagna cheesy dinner. All right, cool. So we come here, for lasagna cheesy dinner, wicked. All right, awesome. So we did that problem. Feeling good. That one's a pretty simple one. I don't know how many points this is. I hope I included it. Am I stupid? I'm stupid. Sorry, guys. I think this is a 5-pointer, if I had to guess. Especially because there's 5 of these. So, yeah, 1 point each square. All right? So now we can come over here. This one's the evil one. So this one's a pretty nasty one, right? So we need to understand how all of the quadratic probing works really, really well to make this work. So suppose we insert 9 strings into a hash table and end up with the following. So here's the hard part. They don't actually tell us the initial hash either. Suppose we no longer know the order in which these strings were inserted or what their hash values were. In solving this problem, you may assume quadratic probing for collisions. This is important during the insertions. You should also assume that no strings have been deleted from the table and that each of these strings were inserted exactly once, no more, no less. You may assume the table length was 13 for all insertions, i.e. none of the insertions triggered an expansion of the table. Fill in the 10 blanks below to indicate whether the hash value for banana, when modded by the table length 13, might have been placed in this value. For example, it's impossible that hash banana mod 13 could have been 1, because if it were, banana would have been there. Do we understand the question, the nature of what we're trying to figure out? Right? So we're trying to figure out all of the positions banana could have been. And so they already fill us in some things here, right? They tell us some that are no, some that are yes. So let's talk about why 12 is yes. It's because banana's there. So of course we have the opportunity that banana could just be inserted at position 12. Let's think about why that it's not position 4, right? Again, if it was there, it'd be there. So we can kind of go backwards here. We know that banana couldn't have been position 11, right? Because if it were, it would be in there. It's the same type of idea that we have going on over here, and the same thing with 7, because if it was 7, it would be there, right? So we kind of filled out the rest of those at that pattern. And so now the thing is, if it's in this current position, then that means there could have been a collision at some quadratic variable to put it there. So what we can do is just check backwards. We could check at 12 minus 1, 12 minus 4, 12 minus 5 or 9, so on and so forth, and keep seeing if we find a collision there, which means it was a possible match. So we go back to 11. We already know that that's not true, right? Let's say we go back 4. So 1, 2, 3, 4. Mango? That could have been a valid spot for us to place this. Because if we did have a hash of 8, or no. Yeah, we would have gone 1 this way and then 4 that way. So this is a valid position, right? Does everyone see how I deduced that this is a good spot that banana could have gone? It's because it's 4 away. So 8 could be yes. So we've checked 4 backwards. Let's check 9 backwards, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Peach, could this have been the position? No, because if we inserted it at peach and it was already there, it would have went to 4. So that's the weird thing about this problem, is you need to kind of consider that as well, because you have to go in increments. So in this case, 3 could not have been a valid 1, because again, we could have gone forward 1 and gone right there. Interesting problem, right? Kind of tricky. So let's go all the way back. Let's go 16 back. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, I miscounted. So sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Could orange have been one of the positions? Well, let's trace it through, just so that we're certain, all the way through. So we're at orange now, right? And this is gesture mode, so that's going to erase. So we're at orange right now. We go forward 1, apple's there. So we're still a good contender. 1, 2, 3, 4, and lime is there. Okay, we're still a good contender. 4, so this is 4, 5, 6, 7, 8, 9. Someone's there. 10, 11, 12, 13, 14, 15, 16. Boom. So orange was a good contender. Orange is someone we can deal with, right? And so now what we could really do is we could go one by one by one and just check each of these to see if it would be valid. So like here, let's hit lime. Let's go to 0 now. We're looking at 0. Okay, we collided. Let's check 1 next. There's an empty space. This couldn't have possibly been it. Let's go to 2. 2's the value. We have a collision. Let's go here for 1. Okay, there's another one. So let's go 1, 2, 3, 4. There's another one. 5, 6, 7, 8, 9. Couldn't have been true. Why? Because we hit 9, it gets inserted. So one by one, this problem is just a matter of, okay, let's just keep quadratic probing and imagining that this was the index. Let's look at 5, 6, or 10 next. Who wants? What are we going to do? Let's look at 5. So 5, go forward 1. We got a collision. 1, 2, 3, 4. We got a collision. 5, 6, 7, 8, 9. Couldn't be the case because we just inserted it. So 5 cannot be one of the valid indexes. Go back here. Do the same thing for 6, and I'm going to speed it up because I think you guys got the message now. 6, move forward. It's been inserted. This can't be a valid position. Let's go down to 10. 1 forward, can't be a valid position. So we have, let's see if I can do both of these at the same time. Look, no, 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 blah, blah, blah. The first yes we hit is 8. The second yes is 9. The third yes is 12. Y'all got that? Y'all see how we did that? That one's a fun problem because I made the same mistake my first time. We're like, oh, it's open. We could put there. But no, you can't. All right. Any questions at all about hash? Hash, hash table, hash function, hash trace, collision, probe, blah, blah, blah. All right. Last but not least, the bonus section. We didn't teach this last year. And guess what? On my exam, we had a permutation problem. So y'all are feeling free to leave or whatever, but you know, who knows what's going to happen again, all right? So I'm going to go through this really quickly. This is like a small little subsection of a lot of the topics we've already gone over, so this shouldn't take too long. I heard the bags rustling, so just hold on, like 15 more minutes, all right? So for generating permutations, it's a really helpful mindset to have of you're either in or you're out. You're going to have this mindset for a lot of algorithms later on too, so try to keep it in mind. And when you have a behavior like this of either you're in or you're out, it's 2 to the n. Because if you think about it, let me go ahead and kind of demonstrate what I'm talking about. So like at each position, let's say we have a permutation A, B, C, D, and we want to find the permutation of this. So for A, there's 2 options. Either we put A here or we don't. We're in or we're out. Same thing for B, same thing for C, and same thing for D. So we have 2 to the 4. And so that's what I mean by 2 to the n behavior, right? So they're probably never going to ask you to write an optimized permutation algorithm or one that performs on numbers bigger than like 6. If they give you an example, they're not expecting you to do some crazy algorithm for this. They want you to brute force it. And so how can we achieve this you're in or you're out behavior, right? I just did the same thing twice. All right. So this is one way to do it. This is the recursive way to do it. Who knows about this whole blah, blah, blah used helper array? I know some professors taught permutation. Okay, good. I'm glad it's that few. Ahmed taught it to me that way. My brain doesn't work that way. But I go over both. So essentially what this is doing, I think it's important to show this tree, right? And so this is what I mean by either you're in or you're out. So we have ABC. No one's been swapped yet. No one's put there. No one's in yet. And here, I'm going to go ahead and swap over here. And we'll go back to the code in a sec to demonstrate this. So no one's been locked yet. We can count the red letter as we've chosen to put this in that specific spot, and it's in. So for right here, we decide A is in. But for here, we decide B is in, and here C is in. Pretty straightforward for one iteration. But then once we have this, we now have two more choices. So here we say, B, you're in. And this one we say, C, you're in. And we're going to keep doing that until, I mean, obviously, B has to be in that position because all of the other positions have already been taken. Everyone else is in. And so do you kind of see how there's this in or out mindset here? So for this one, we pick B first. And now we have between A and C. So A and C. You're in, you're in. Do you guys kind of see that? That was the mindset change that I had to understand permutations. So here's this, right? So we're saying, look, if start equals size minus 1, this means we're at the end. We have no other positions to mess with. We're going to print it. Imagine that just prints the whole array. But this is the actual, like, the chunk of everything, right? So this is size. You can imagine that this is the length of the array if we're doing numbers, or the size of the string if we're doing permutations of strings. This right here means you're in. We're setting each character, because remember, we're iterating over all the characters, and we're saying A is in, and it calls it. And then it goes all the way down the tree until we hit this, right? So you're in. And it continues down with it being in. Now here's the kind of stupid, crazy part. But this right here is called backtracking. And I don't know about you guys, but I heard that they said that there was going to be backtracking on the FE. This is the only time we've seen backtracking is in permutation. So we fix it in. It's in. We iterate all the way down. And then when we iterate back up, we take it all back out again. When we iterate down, you're in or you're out. Because if you think about it, right, if we don't swap this back, then that position will show up in every single, like, we will never go and generate another permutation. Like, A will be the first in every single iteration of this. So we need to take it back out. We need to unlock, right? And so if you guys know this whole used helper array thing, it's literally the exact same thing, but instead of swapping them, we use an array of ones and zeros, where the 1 represents you're in, and the 0 represents you're out. You guys, again, it's that kind of mindset. So in this case, if we're at the thing, we're going to print, right? We're going to go print the whole thing. They use true and false here. For C, I'm pretty Booleans aren't even, you just use 0 and 1, right? But essentially we're saying, hey, this array right here, if the element has not currently been used, let's put it into our array and generate. And this is us saying you're in. Question?
So essentially what we're doing is we're fixing like one element and we're swapping the two elements we haven't fixed yet.
Yeah, so you're choosing an element to fix and you're putting it at the rightmost non-fixed position. So you're basically you're making it the next fixed one. And then you generate all the way down. And so that'll generate you a permutation. But then again, remember, the file format into a way that it will save the recording. We're safe. Okay, awesome. The computer went to sleep? Y'all got my mug. Hello. We're still recording. Okay, so back to what I was saying. Let me make sure my iPad's sharing the screen. Hold on a sec. And he's joined back my own damn Google Meet. Share screen, entire screen, start. All right. So you can kind of, again, treat this as you're in or you're out. You guys kind of see that? Have that understanding? Any questions about this before we move on? Okay. So we have two types of permutation problems that we've seen in the past. I'm only going to do one of them because I get the feeling y'all want to get the hell out of here. Are y'all okay with that? But I'm going to do the harder one so that, you know, if you guys can solve this one with me, then you can probably solve the other one, okay? I'm just going to go over this problem and explain how we would solve it conceptually before showing the answer, just so y'all leave with that knowledge. So finish the function below so that it determines the number of permutations where each adjacent element is, there's a gap property. So look, this is the one that has the used array. So we have our used array and our current permutation, an integer k, which is the current empty slot, and we're given max gap. So what this is saying is we aren't allowed to generate a permutation if each adjacent element isn't within max gap of each other. So let's say we have 1, 2, 3, 4, 5, and max gap is 2. So I fix 1, right? And let's say we're at the part of the iteration where we fix 5. This would not slide because this has a gap of 4 and our max gap is 2. You guys get that? All right. So the way you would do this is you would basically generate a permutation. So again, we're checking first right here of saying, hey, before we fix anything, we got to check, hey, is it within that range to be fixed? If it's not, let's continue. So we're iterating over each element, 1, 2, 3, 4, 5, and we're saying, hey, if the absolute value right here, if the difference between the two, so of our current index minus 1, or minus the number we're currently on, then continue. We're not going to use this as one of our fixed elements. And then this is basically the exact same thing I just showed you. Again, we fix it, we call the solution, we take it out. See how that kind of works? And then when I say we place it, we're putting it in this array. And the reason we're adding it up is it's because it's asking us to find the number of close permutations we have. So if we reach all the way to the end of a permutation, then that means we found one valid permutation and we add it to our return. Cool? All right, so now for the tic-tac-toe problem. Has anyone seen this one before? Yeah, I've heard there's like rumors about this damn problem. This is one that Leo and I had to solve. This was May 24. This problem is, I don't even know why this was on the FE. So essentially so long story short, forget that wall of text, right? It has to be recursive. And you have to determine with a given tic-tac-toe board, can X win? We don't need to know what position X needs to place to win. We don't need to know at what turn. We just need to know, is it possible for X to win? So now you're probably like, why the hell is this a permutation problem? So I'll break it down and I'll go into it and show how, at the end of the day, this really is a permutation problem. So here's some things we can extract, right? Note that a board is a 3x3 array of integers. We would expect that much. It could either have empty, X, or O. We're given constants to deal with those type definitions. So we can do empty, X, or O, right? The three given functions return the current state of the board as it is from the player X's perspective. So we're not thinking as O. We want to think as X here. It doesn't want to know what could happen in the future. My turn is 1 when it's X turn, and 0 when it's O's turn. So we have a variable to know whose turn it is. I will say you will have to place and unplace X's and O's in your solutions. This is them literally telling you. Remember, you're in or you're out. You're placed or you're unplaced. That line was the hint to tell you, hey, this is just a permutation problem. If you think about it like that, it's a lot less complicated. So you're either in or you're out. The intention here is that player O plays pessimistic, meaning it will always make the wrong choice. Because if we had to deal with multiple choices from O, then we would have to do like an actual like real backtracking algorithm. And this is just a permutation, right? So any set of moves that X and O can make from the current state result in X winning, it should return 1. So this is just true or false. Can X win? Yes or no? So how is this a permutation function? So here we have 3 functions that are they're helpful for us. X win, X lose, or tied. It's a true or false function given the board that'll tell you whether or not X wins, X loses, or is tied. Pretty straightforward, the name's here, and it gives you the function. Question?
So like, I originally thought this would be kind of similar to a flood fill problem because I assumed like the board would be filled, and then when we get to an empty space, we check if X could win or if O could win there. So like that's how I originally like went about it. Like what would like, this is what I'm asking is like, what in the question would distinguish it as a permutation problem as opposed to like a flood fill problem?
So it's because of the place and unplace.
Okay.
So imagine if you wanted to do it flood fill, you'd have to do it this way. You would have to flood fill all the way down, recurse all the way up, and then flood fill again with a different pattern. And so that's why it's like flood fill might not be the best choice, because you can, at every position, you can either put X or O, right? And so it's like, uh-oh, you know what I mean? Like, it's too complex for a flood fill.
In the place of the problem, so permutations are just checking like every single possibility. That's kind of what they want you to do here. Or you could think of it, if you check every single possibility going from the current board, then yeah, we could find if X is going to win. If X can win, right? Or if X is going to tie, or if X is going to lose.
Okay.
So
All right.
just basically, if you have to check every single possible variation, you could think of it as a permutation question.
And then one more thing we have to consider, they put it nice and bold underline, because this is probably not that hard to do in a for loop, right? Functions that do not use recursion will receive 0 points. What do we need to do when we start a recursive function right off the bat? It should be like clockwork. Base case. So what are our two base cases here? Well, the first one is if we're screwed. So if X lose, or tied. So this is like, hey, we're done. There's nothing we can do here. You're screwed. Let's just back out. So we're going to return 0. Right? Because we're trying to determine can X win. What's up?
Is there a null check specified?
For these, we don't have to do any sort of null check because we're working with an array. We could assume that all of these handle, and no, it's because there's also, the board is full. There's also an empty value. So like there will never be a cell that is unpopulated. It's either 0, 1, or 2. And they give us these type defs to make things a little easier for us, right? Okay. Now, we have another case that we hit before we even want to continue, right? If X can win at this current state, then what do we want to do? We want to say, hell yeah, you can win. Congrats. So now here's the question. Where does the whole permutation thing come into here? So let's just start maybe writing out a permutation, right? We need to, our goal is to, 1, generate every board. Now that's a big goal. So how do we break that down? For each position, place X or O, depending on whose turn it is. And then we recurse. That's essentially where it's the whole permutation problem. So let's loop over all of the positions of the board because we need to be able to place all of them. So we're going to go to 0. We're going to go up to 3. Right? And then we're going to go through J. Why are we doing the double nested for loop here? 2D array. Exactly. All right, so now we're now inside of this loop, we're going through each position. So what we want to do is we want to place into the board, like if it's empty, right? Because we need to, if it's not empty, we obviously can't place anything there. Tic-tac-toe doesn't work like that. I can't take his X and put my O. So we're gonna say if board I of J equals empty. They gave us a definition at the top, and you should use it to kind of keep track of your thinking. So we're only going to continue doing something if the board here is empty. And so what are we going to do? We're going to say board I of J, and we can use a ternary here. You could do a if else here, but I don't have enough room. Essentially what this is doing is if my turn then we put X, else we put O. Do you guys see how the ternary sort of syntax works? That's really helpful on the exam when you have a limited room, but you could do if my turn, board I of j is X, else board of I of j is O. You guys follow how that kind of works? All right, just to shorthand it. So we've now set it to that specific point, right? Now what do we need to do? And I want the audience to answer this. So we fixed it.
Check it for commit.
You can do that, or
So we could check it.
you could just pass it on to the next iteration, since at the top, that would just return 1. So instead of saving your time in the loop, we fixed it. Now let's generate. Let's see, can X win? And then we do board. I forget what the function signature is. Board, and then what are we passing in as my turn?
Oh, his turn? So not my turn?
Not my turn. Exactly, because we need to alternate the turn. And now, right before we get out of this loop, there's one more thing we need to do. So you're in, you're out. So now we need to set this back to what? Now at the bottom, right? We need to go down here. And how are we like actually successfully returning all of this? Wait, what the fuck? Yeah, the base case will work. It will return all the way up. But what happens if we reach all the way to the end and we haven't returned anything up here? Like nothing's happened here. 0. That means X lost. Because if we haven't returned something all the way up at this point, then yeah, X is lost. Yeah, we would, yeah. So see how that kind of works? So this is just a permutation problem. But in the middle here, we also have to return this if, yeah. If can win, we return 1. See how that works? We generated every possible permutation of tic-tac-toe. Either you're in, you're out, place it in, took it out, kept generating, returned. Sound good? All right, with that being said, there you go. We're done. Thank you all for coming. Thank you all for sticking around. I know today felt really, really long. We lost like half of people here. I'm going to post this in the Discord another time. I really want to get your guys' feedback. I have an idea of what some people are going to say, but we want to extract as much insight as we can out of these events so we can continue to do good ones. Good luck tomorrow. Get a nice, good rest tonight. Has Guha sent you the information yet?
Yes.
Okay, thank God. Go ahead, get a good rest tonight. And yeah, good luck. Have fun.